Good morning. We'll start in a couple of minutes. I'll give it a bit more time for people to join online. But can someone online please confirm that they can hear me? That would be helpful. Thank you.
I can.
All right. Thank you.
Yes.
Great. Okay, let's get started. All right, so good morning and welcome to this training on MLOps on HPC. So this is a training which is organized by the Flemish Supercomputing Center in collaboration with EuroCC Belgium. So yeah, that being said, this is a QR code which you can sort of ignore if you want. Basically, it points you to a web page, which I'll show you in a minute. But I'll also put a link in the chat because that's way more convenient for those of you online. So let me quickly do that and tell you after that what's on this page so that you know what it is about. Okay, so here you go. So that link actually brings you to a very small website. That website contains some information about this training, about what to expect, etc., which is all sort of, well, uninteresting. What's most interesting actually is this link to a GitHub repository. And that contains, if I manage to click correctly, then it contains the slides for this presentation or for this training. But more importantly, also directory source code, and that contains all the source code used to experiment with, to develop this training and so on. So feel free to clone this repository, fork this repository, whatever you like. It is something. Just a second, is this okay? I'm just on the wrong page. Okay, sorry, page swapping things. Basically, feel free to fork that repository, clone that repository, whatever suits you. It is very liberally licensed, so you can reuse it as you prefer. Okay. That being said, another QR code, in this case to join us on LinkedIn. It's always a good idea to follow us for news about trainings on the one hand, but more generally on HPC stuff happening in Flanders and abroad. well, Belgium and abroad, let's put it that way. So basically, it's always a good idea to stay in touch with us, to keep up to date. Okay, then some practical things. First, some conventions about the slides. Basically, when I have code or a file name or something like that in a running text, I'll typeset that in a ugly looking monospaced font in order to make it stand out a little bit and make it easier to distinguish between running text and the code or whatever. Larger fragments of code, same font, but on a grayish background. If there is a data file, I'm not so sure there are any in this presentation, but regardless. So again, same font, but different color background. And what you will see from time to time are these ellipses, which basically means not enough screen real estate in order to put everything on the slide. If you see that for data files, well, it's pretty straightforward, just more of the same synthetic data, so who cares? For source code, don't worry either, because again, all source code is available in the repository, so it is easy to check. Or alternatively, it was explained on the previous slide, or it will be explained on the next slide, or it is completely irrelevant. Okay. Other conventions. Everything that happens in the shell happens on a black background, again, to very clearly distinguish what happens. So this is a terminal representation, which basically means that the $sign here is, of course, just a visual reminder that this is a terminal command. And of course, you are not supposed to type that, it's just a visual marker for that. A few icons occurring throughout the presentation. Good practices, guess what? Then thumbs up. Bad practices. This cute-looking bomb means potential for disaster. Disaster in the sense of things that crash, things that will do very unexpected things if you are not aware or if you're not careful. Then there is also performance issues represented by this snail. It looks cute, but yeah, you don't want to meet it. And then general warnings and so on. So that's fairly straightforward. Two more practical things. If this is interactive, it's nice for me. That's much nicer for me to give a training. It's also potentially a lot more interesting for you. So I would encourage you, if you have questions at any point, just ask them. I'm very happy to answer them, to start a discussion, no problem. For the people online, just put it in the chat, and I'll keep an eye on the chat at all times. So basically, I hopefully see or even hear when a question is posted. So feel free to do that. It makes hopefully everyone's life more interesting. The last practical thing I should mention is about the recording of the training. So this happens as we speak, but I will not make this recording public for a very simple reason. As I said, the chat is visible at all times. It's also being recorded, which basically means that names will be visible. Names of participants are going to be visible from time to time. And I don't have your permission to publish a video that contains your name, so I can't and won't do that. However, the recording is going to be uploaded to YouTube as an unlisted video. So if you want access to the recording, no problem, just send me an email and I'll send you the link to the recording. Keep in mind, this recording is being made using Blackboard. So Blackboard needs to process this. This is more than 3 hours of video, almost 4 hours of video, so that takes a while. Then I need to download it, which is pretty fast depending on where I'm physically at. But then I need to upload it to YouTube, and YouTube needs to process it. Again, the same duration, that takes a while. So story short, it will be available like this evening. So, but drop me an email if you want access. Okay, so that's about the practicalities. So let's start with little introduction and then go ahead. So basically, machine learning is increasingly important. I don't think we need to be modest about that. It's not only important as a research topic by itself, but also it's being used in applications, also in domains that traditionally had absolutely nothing to do with machine learning. Think of computational fluid dynamics or other domains which traditionally have little or no machine learning. Nowadays, with surrogate models and so on, it is definitely a topic of interest. So that is pretty straightforward. Now, if you have done a machine learning project at some point in time, then you might have noticed that that is not necessarily trivial to reproduce because of several issues. Most of them we will go into during this training, but basically reproducibility is not really a trivial thing. Why? Because there is a complex setup which needs to be replicated in order to be able to reproduce something. So yeah, it's not trivial. So we need to discuss this a little bit. And then, of course, it also requires sufficient flexibility in order to experiment. Because you try something, doesn't work, you try something else, doesn't work either, etc., etc. So you iterate until you get a reasonable level of success by whatever measure that might be. It might also be that you run out of patience and just start doing something else. But anyway, so that's essentially been motivation for a buzzword. In a way, more than a buzzword, but yeah, I mean, it's all AI nowadays, so basically it's called MLOps, machine learning operations. The inspiration taken from DevOps, development operations, blah, 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 the usual thing. But okay, you could say, yeah, we have DevOps, why do we need MLOps? There are a few things which make this different in a way. Now, I have been introducing this starting from the point of view of machine learning, but in fact, the whole presentation or the whole training is not going to be about machine learning. It's going to be about doing experiments, and I'm now making this a bit more abstract, doing experiments that depend on parameters, that produce metrics, and that you want to reproduce over time. Those experiments may or may not produce artifacts that you want to reuse, etc., etc. So that is, at a more abstract level, exactly the same thing as I said about machine learning. Okay, but that basically means that I would very much prefer to call this training XOps, which is a term I invented myself, experiment operations, because it is much more general than just being limited to machine learning. Of course, for marketing purposes, and because no one has a clue what XOps potentially could be, so you don't get any people in your training. So basically I called it MLOps, but yeah, this is much more general. So if you do experiments just using, no, not just using, that sounds derogative, it's not intended as such, but using classic HPC software, you have a very similar workflow. So basically formalizing that workflow, supporting that kind of research, using tools that are now being popularized in the machine learning world is maybe not such a bad idea. So for me, this is about XOps rather than MLOps. For those of you who specifically come for MLOps, no worries. It's all applicable, no problem. It's just that there is that extra abstraction layer which allows you to use the same framework, the same frame of mind, if you want, to manage non-machine learning experiments. Okay, so there are quite a lot of options out there. So basically there are rather specialized things like MLflow, like ZenML. So those are frameworks that have been specifically designed to do machine learning operations as such. And there is absolutely nothing wrong with them. The only point is that they require a setup which is not necessarily friendly towards HPC. Because in HPC, what do? We submit batch jobs. Those batch jobs do our experiment. They train our model, they do some inference, whatever, if we are back into a specific machine learning context. But basically, that's how it happens. It happens non-interactively. That's why you use an HPC system. So yeah, that means that if you have a system, a workflow system or an operations system, whatever you want to call it, that is compatible with HPC, it means that during the computation at least, all this supporting stuff needs to be up and running. Okay, you can do that. It's possible. I mean, workload managers such as Slurm will support heterogeneous jobs. So one part of your jobs could be spinning up an MLflow daemon, while another part of your heterogeneous job, the second part, would do your actual experiment. And that would sort of work. But yeah, does it make sense? Well, actually, no, because the big added value of these MLOps frameworks, utility stuff thingies, is essentially that it allows you to also analyze your experiments after they have been done. So you need the stuff running while your experiment runs in order to record stuff, but you also need it afterwards in order to analyze your stuff. Okay, but then your job is done. So where's your daemon going? Yeah, it's done. Do you somewhere have a server to run it on? Okay, fine. You're perfectly happy to do that. And you may even get it to work with tunneling, etc., etc. So it's not impossible. But on a typical HPC system, it's not really a good match. So looking for something that actually will work nicely on an HPC system, there's also DVC that has a long history. I have been mentioning it in trainings for years, but usually trainings about version control, which is, of course, at the end of the day, the bloody same thing. I mean, you want reproducibility. So what is DVC originally? DVC originally was Git for data. Okay, we'll talk about that in much more detail in a minute. But that's what it originally was. And then, of course, the DVC developers noted, oh, there is this very nice hype about ML operations. Let's jump on the bandwagon. Which they did, which they, in my opinion, did quite successfully. So basically, that means that now DVC is quite a bit more than just data versioning. It is now also pipelines, experiment management, experiment queries, comparing experiments, etc., etc. Without daemons, without frameworks that you need to set up. So, that's rather nice. That maps quite well on HPC, rather than MLflow daemons that need to live somewhere, wherever. You have something that you can just deploy on an HPC system. It does its thing while you're running your job, and afterwards you can, on your local machine or whatever, after synchronizing a number of repositories, you can just analyze your experiments. Easy. Okay, that sounds good, and that's why I'm going to talk in this training about DVC and exclusively about DVC. It's a technology choice. You may question it. That is, you are certainly 100% at liberty to do that. I would say if you're really into machine learning and you have the infrastructure to run an MLflow server, feel free to do so. However, most people haven't, so that's why DVC was the weapon of choice in this particular case. Okay, so DVC stands for data version control, and that, as I already mentioned, that's its origins. That's where it came from. That was its raison d'être when things started out. Okay, so I have been liking it for quite a while for a number of reasons, and then I'm purely talking data versioning. So basically, it interoperates with Git. Since I like Git for version control, that's very nice because that basically means that DVC, if it interoperates with Git, I'm going to be happy. Okay, it's even very much like Git. So conceptually, it's very close to Git, which is nice because that means I need to learn only half a new thing rather than a completely new thing. Okay, also I need to remember much less than having yet another tool that does something completely different with a completely different philosophy. So that's great that you have this close integration between your code, let me call it this way at the moment, code versioning system, Git, which you're familiar with, and your data versioning system, which is DVC. So that's rather cute. And the nice thing is that Git in combination with DVC is indeed standalone. No daemons, no nothing, no things which really, really complicate your life on an HPC system. Okay, and DVC supports remote data storage. What that means completely, I'll talk about in a minute. But basically, your data can live somewhere, not on your HPC system, not on your laptop, but somewhere out there being defined later. Okay, so it has quite a number of features. The first feature is really trivial and obvious. Well, still, but it's really obvious. It does data versioning. Yeah, that was what it was originally designed to do. So yeah, of course it does it. But nowadays it also does data pipelines, and we'll see how that works. Experiment management, and then something that is a bit fishy. It also does model registries, but not unless you pay. Reasonably expensive fee in order to do model registry. Okay, do you really need that? It depends. You can get around that with other ways as well, but yeah, that is a bit of a drawback, and that is of course something that frameworks such as, or tools such as MLOps do give you without you having to pay, in the sense that that is totally open source. This DVC Studio thing is definitely not open source, and it's definitely a paid service. However, well, everything I'm going to talk about today in this training are things that you can do with DVC without having to pay any fees. So basically the open source part, or at least the free to use license of DVC. So that is, as such, not a problem. Is this a bad thing that they charge for certain services? Well, maybe not, because basically that will earn them some money, which is good because then they can accelerate development, which basically means that we get a better tool. So, okay, I can live with it, and I can work around it if I want. So, whatever. I'll mention that later again. Okay. So, let's start just with data versioning, because yeah, that's its origins, and that's very useful by itself. It is something that you can always use. But maybe, do I have a motivational slide for that? I should have. Yeah, probably here. Yeah, indeed. So basically, this slide is just about setup. So that means that you need Git. It also means that you need DVC. So for people on the KU Leuven system, there is a module. Well, Git is just installed in the images. It's there, so you don't need to load any modules for that. My colleague Ezan was kind enough to provide a DVC module, which you can use. If there is no module on your system, or if you prefer not to use a module for this, and there may be valid reasons, very good reasons not to do that, what I typically do for this type of software is using pipx. That's a sort of pip installer, but specifically for applications. So you don't use it to install Python packages. You install it to use only Python packages that are applications. And DVC happens to be one such application. So after installing pipx, which is easy, you can just pipx install DVC, and then essentially you are sort of good to go. Not quite, there's a small pitfall, but apart from that, you are good to go. Does this have advantages, disadvantages on HPC systems? There is an advantage in this particular case, but in general with Python applications. Maybe it's a good idea to just show you which applications I do install using pipx. Now, where are they? If memory serves, they're all here. Yeah, that looks good. So these are basically the things which I manage with pipx. So for instance, you recognize DVC. So that's one of the things. But you also recognize things like Flake 8 or Black or Rough. Those are tools which are specific for Python, but I kind of use them in every Python project because I do want to check for compliance to PEP 8 to statically validate my code with Flake 8 or with Pyland, or I want to format my code with Black, or I want to do both of them with Rough, whatever. So basically this is a set of tools that I typically use in each and every of my at least Python projects. And as you can see, there's also stuff like DuckDB for quick experiments. There is a Fortran package manager. Yeah, indeed, it does exist. So basically, these are all essentially Python tools, but installed using pipx. So pipx. So basically, that decouples my tool set from my projects. And that also means that I have much more liberty to combine things because these pipx applications don't interfere with one another. They have their sort of own virtual environment created automatically. Don't have to do that, happens automatically. And basically I can make sure that they run totally in isolation. So yeah, that's the way I work on my own system and also on the HPC system. So should you do that? It depends. You can, if you like. You can simply use a module if you prefer that. Why don't I use a module? Well, because then suddenly my Python version is spent. And if I load another module and I need a different version of Python, all hell is loose because then Python path suddenly points to different things than DVC expects, and you are in a very, let's say, interesting situation, where interesting means that you get all kinds of very nice errors which you haven't got a clue where they come from until you realize that you're mixing environments. So yeah, that's why pipx is useful. Okay, that being said, long introduction, let's have a look at the slide. So basically, this is a very basic setup of DVC. So those are the steps. If you have a Git repository, that Git repository relies on data. Let me put it that way. How can I put that data under control of DVC? That requires a little bit of setup, just like you set up a Git repository. So basically, these are the steps here. And I will be brave and try to replicate them without messing up too much, which is always a bit adventurous, so bear with me. So basically, as usual, you start with a Git repository. I'm not going to follow the slides here. I'm actually going to first create one on GitHub. There is a question in the chat, apparently. Let me read first. Yeah. Yeah, so basically, yes, pipx applications are global. They will be by default installed in your .local bin. So basically, yes, you can use them in any circumstances. Okay, so then the question is, how do you isolate it from your libraries installed in your specific project? For instance, preferably not via pip, but maybe via something a bit more easy to use is not the word, but something more reproducible like Conda or like UV or whatever tool you prefer in the Python world. So how do you keep them separately? Well, you only potentially have to take a little bit of care with your pipx tools. The thing they should never see is Python path, the environment variable Python path. So that's something that you have to be a little bit careful about. So there are a number of ways to ensure that that's the case, that it doesn't see that. And basically the simplest way is to say, okay, Python path is the empty string, and then dvc version, whatever. Don't know whether it supports version, but I think so. Okay, so this isolates my application, whether it's DVC or any of the other tools I mentioned, from my environment, for instance, a loaded Conda environment, or a Python module, or whatever. So basically, the only thing that can interfere with a pipx application is Python path. So the easiest thing is to, in your .alias file or your .rc, depending on how you are working, to just define an alias that maps DVC to either this, or what you can also do, that would be the same thing, is env -u Python path DVC version. I hope I have it right. Let's see. Doesn't complain, so basically it's likely correct. So essentially this env-u thing filters out Python paths from the environment, which is passed to the subprocess, or the subprocess which will be DVC. So that's a way to filter your environment, to tailor it to certain requirements. And this, of course, is local. So both the first form and the second actually ensure that this Python path is not modified. It's only either modified for the command which follows it, or with env-u, it's the environment for the command that follows it, which is from which Python path is eliminated. So yeah, this is, in my opinion, rather neat. There are a number of other caveats where you have to be a little bit careful, but in general, that's how that works easily. Okay, so what I wanted to do was to create a GitHub repository first, and then use that as a remote. So I'm doing this on GitHub. I'm doing this in my personal namespace. You can do that in using GitLab on-prem for if your university has that, or your GitHub organization, if that's what you do. Talk to the RDM people for that. Basically, they should be able to tell you. Okay, in this case, it's going to be in my personal namespace, and I'm going to give it the my favorite repository name, which tells me that I can remove this as soon as I am done with this. But it already exists. That's annoying. Okay, let's call it to remove to then. Okay, I don't need description, I don't need blah, I don't care, I don't care. The only thing I care about, where is it? Whether it's public or private. Normally by default it's public, and that's what I want in this case. I don't care. So yeah, I think it's fine. But where can I choose this? That's weird. Okay. All right, no git ignore. Let me make my life a little bit easier and just use the Python template. Then it's there automatically. Okay, whatever, add readme. Okay, apart from that, I don't need a license. That should be it. Where can I say it's public? That's weird. Private. Okay, anyway. Okay, so I've got my repository, and of course, now I can just clone it locally. Yeah, well, maybe if I paste the URL after that, that would be very smart. Okay, so to remove to, okay, I now have a Git repository. So basically, that means that the first 3 steps here, making the directory, cding into it, doing git init, have all been done for me already, because I just cloned an existing repository. This is my typical workflow. So it's if you start with a local repository, so without a remote, and you want to add one later, that's very easy to do with GH, so the GitHub command line interface. But typically, I prefer this approach. It's way simpler, and I don't need to think about it. Okay, so we do a DVC init. Let me first do a git status. Everything should be clean because this is a fresh cloned repository. So yeah. So now I do DVC init. Okay. And then you see that it prints some version information, etc., etc. Apparently, by default, it does anonymous usage info. Yeah, okay, I can live with that. There is likely a command line switch to switch that off, but okay, let's not go there. Okay, so that's nice. Let's have a look what happened in the repository. So git status, and you see that there is some new stuff here. Okay, so the new stuff is a .dvc directory in which there is a number of things. We'll look at it in a second, what's there. But anyway, what is here, this is something that I definitely want under version control. That's for sure. And as you can see, this is already staged. So DVC has not only generated these files for me, which is great, but it has also immediately staged them for the next commit. So again, there is quite a bit of integration between DVC and Git. So indeed, the next step now is committing all these files. Okay, so git commit with some message, initialize DVC. Okay, my status is clean, and let's have a proper look in the DVC directory, and then you see that indeed there is this config file. Yeah, we committed that. There is a git ignore. We committed that as well, and there is a temp directory which we did not commit. So that is going to be in the git ignore, which we just committed. Okay, so all of this is automatic in a sense. We don't have to worry about it. And of course, you only have to do this once per repository. Okay, so we're almost good to go. Then we need a little bit of configuration. So basically, if I want to add a remote, so essentially, if I want to make sure that my data is stored somewhere else than in this directory, then I can do that by adding a remote. And in this particular case, I'm going to do that in a very trivial way. I'm just going to say, well, okay, I do DVC remote add. Okay, it's going to be the default, that's the -b. And the name for this remote is going to be local storage. So that means I'm just going to use a different directory in order to have my data stored. And in this particular case, I just go one level up, DVC data. So let's first create that directory. I don't remember whether it's created. If it's not, yeah, we can try, actually, why not? DVC remote add -d. Let's call it local storage. That's quite descriptive. And then in the parent directory here, I do DVC data. Was that the one I used? Yeah, okay. So let's see. Okay, so let's have a look whether that actually happened. So if I list the directory, there is no directory. That is a little bit disconcerting. So basically, I would prefer that that directory exists. So let's create it just to make sure. Okay, that's not in the slides, so I think it would be smart to add this. All right, so let's again have a look at Git status and see what happened. So something's changed. As you can see, what was modified essentially is just DVC config. So that one is changed. Yeah, indeed, if we would look at it, we would see that there now is an entry for the remote we just defined. So I'm quite happy with this, so I'm going to commit this. Git commit -a-m add local directory remote. Okay. All right. So I've added my remote, and then I've done it in one go here. I had a git add followed by git commit. I just did git commit -a, which is the same thing. Okay, so now everything's clean again, and we are in fact ready to start using DVC. Okay, so that was easy. Essentially, one step that you really need to do, DVC init, committing the stuff, and then adding remotes. I'll talk about remotes in a minute, because just adding a local directory as a remote is nice for demonstration purposes, but it's not something that you would consider extremely useful. Okay, so remotes, because that's part of the interesting stuff. So yeah, okay, wait, let's take a step back. Why on earth are we complicating life? Because at the end of the day, why don't we just store our data in our Git repository and be done with it? That would be way easier, no? I mean, why are we even bothering with DVC for this? Well, the problem is that your data is likely to be quite large. If you are in a machine learning context, then your data is probably a couple of gigabytes, and it might be way more, which basically means that you are not going to be a very, how shall I put it, happy user if you control this with Git, with version control, for several reasons. One reason is that there are definitely limitations on repository sizes, and they are way below whatever reasonable sized data set. So you can't store the data set in the repository because it's too large. That's one reason. Suppose that you could store it, it would always be a little bit on the edge, but okay, suppose you could store it. It would also make operations slower. If you clone a repository, it would take quite a while to clone it because, yeah, I mean, it's lots of data. So for several reasons, you would be rather unhappy. So, okay, that's a pity. So that's why DVC is there. So it allows you to couple your data versions, not store your data, but only the metadata for your data in the GitHub repository, or in the Git repository, let's be general, and store your data elsewhere. Okay, so the elsewhere, that's what remotes are about. And you can have one remote or multiple remotes or even no remotes, then it makes less sense, but you can have as many remotes as you like. Okay, so there is also yet another reason why Git and data are not necessarily good friends, and that's because data files can be binary. They can be images, they can be HDF5 files, they can be Parquet files, whatever, but it's binary. And Git and binary files, it works, but they're not good friends. Okay, so in general, you don't store binary files in the GitHub repository. You can do so, and actually, those of you who are rather at REM will notice that I have been doing this because this presentation is on GitHub. That presentation is a PowerPoint presentation. That's a binary file. So yes, you can do that. The problem is that you lose quite a lot of benefits of version control with Git. Why? Well, I can't diff two binary files. That just doesn't make any sense. So if I store something binary in Git, it's just as if I'm storing large atomic copies of it, one copy for each version. Well, copy is then not the right word. One big binary blob for each version that there is. And that, as such, is potentially going to increase your repository size considerably. So yeah, that's another reason why it's not a good match. Okay, so that's where DVC comes in. Basically, DVC generates meta information that you can store in your GitHub repository, because that's just text files, and they will provide the link between your data versions and your commits in Git so that things get reproducible. So that's essentially the approach. Okay, now the data itself also needs to be stored somewhere, because I want potentially to clone my data. Not the right terminology, but you see where I'm going. So basically, I want to use my data not only from this repository, but also, which happens to live on my laptop, but also from the HPC system. So I need to do a different clone. I also need the data available there. So if the data is on my laptop, yeah, that's not going to work. If the data can't be in the Git repository, it needs to go elsewhere, and that's where the remotes of DVC come in. So you have quite a number of options here. You can use a local directory. And for instance, on an HPC system, that might make a lot of sense in a way. Because I could just point it to, for instance, K11 systems, a large staging directory that I have. And there make a subdirectory in which my data is. Nice, I can even share it that way with my research group. Easy. So it seems as if local directories don't make sense, but don't be fooled. They have their very valid use cases. You can go a step further and use SSH or SFTP. And then, of course, things get really interesting, because basically that means that if, again, I would use a directory on an HPC system, okay, by construction, typically I can access that using SSH, so SCP or SFTP. Oh, that's great, because now, all of a sudden, my dataset resides on my HPC system, but if I want it on my laptop, I can just add a remote using SSH/SFTP protocol, and magic happens. I can pull data from the HPC system to my laptop, or I can push data from my laptop to the HPC system. That's nice. Okay, it also supports different protocols. Via HTTP, it supports WebDAV. So if you have some storage thing that supports WebDAV, okay, you're good. I don't think there is, yeah, maybe Tier 1 data might support that actually, but okay, that's a specific VSC thing. And then there is also a lot of cloud storage which you can actually leverage, and that's typically via S3. So that's typically S3 buckets which you're going to use in that piece. Yeah, so basically with respect to iRODS, the RDM team is working on DVC support for iRODS. So it is coming. I don't know at which stage they are right now. I discussed it a month ago with them, and or they mentioned that they were doing it because they knew I was interested. So I don't know the current status. It's, well, I do know it's not released. What I don't know is when it will be released. But it's work in progress, active development. So yeah. Okay, this is cute. This works nicely. So basically, I'm not going to talk how to set up a remote for S3, for Amazon, for Google, whatever. If you're interested, the documentation is very explicit. So just pick your service. There is a recipe on how to do that. It's, yeah, just following the recipe, and there are a million recipes. No, okay, not a million, but there are at least 20 or 30 for different cloud services and so on. So I'm not going there. What I will show you though is SSH and SFTP. Local directory you already know how to do. I just showed you that. Okay, so DVC and remotes, a couple of examples. So the local directory thing is repeated here in a sense. So basically, in this case, again, I'm creating a remote or adding a remote if you want. It's going to be the default. The name is, again, local storage. You can't have two remotes with the same name, by the way, so this is considered this different system. And then you can specify something, for instance, in your data directory or on staging or whatever you like. Okay, so basically, if you want that to be accessible via SFTP, for instance, well, it's very similar. Again, remote add. In this case, the name would be VSC and SSH, etc., etc. So essentially, you get an SSH protocol URL. So same as you would usually use simply for opening a file in Vim, a remote file in Vim or whatever thing. Okay, so you just have to specify your user ID, the login node, and the path to whatever data directory. That's nice because basically that means that I have now a remote which I can access from the HPC system, from various HPC systems, and from my laptop, etc., etc. The whole thing is governed by Linux permissions at the end of the day, and of course it will be protected in flight because it's SSH. So basically, if I have an agent running on my system, this is all really transparent. It works quite easily. Okay, so again, for cloud access, just see the documentation because, yeah, there is too much around. Okay, so this was just set up, just about DVC. Is this more or less clear? Is the philosophy of DVC, its approach to try and tackle a problem clear, and why that there is a problem in the first place? I've tried to explain it, but if it's not clear, let me know, because this is it's useful that we're on the same page here. Otherwise, things get interesting later on. Okay, seems to be clear. Perfect. Yeah. Okay. Okay, how is this related to Git LFS? So basically, that's for large file storage on Git. Yeah, it's something that you can use. I think that you will be able to use LFS as a remote I'd have to check the documentation, I don't know. But I've never used LFS myself because, yeah, you have to pay for that. I don't want to pay for it. So basically, I'm not using it. But if you are an LFS user, then of course things get a little different. Because then you can consider storing your data in LFS. As long as you have sufficient budget, you can actually do that. And then you might not even need to bother with DVC. But yeah, it's at a cost, so whether you want to do that is a different thing. Okay. And also that really ties you into GitHub, of course. So yeah, whether you want that or not, I'll leave to you as a decision. Okay, what did I do? Okay, this I did do. I noticed that I didn't add animation to this presentation. Yeah, but anyway. So now, how do we add data to DVC? Yeah, then first we need some data. That's always nice. So let's create a bit of data. Okay, that will do. Right, I have my CSV file. Great. And now I want to add that to DVC. So quite straightforward, DVC add data. Okay, so as you can see, several things happen. So basically, as you can see, adding has taken a while. So basically that means that my file now has been cached. So it's copied somewhere, scroll away. Well, it's not scroll away, it's still there, but the representation of it, let's put this very general, has now been added to the DVC repository. Okay, why this pops up when I put myself explicitly on no disturb is beyond me to understand, but okay. Anyway, so basically that has happened, that's great. And of course, this was really, really fast because this was a really, really small file. If this is a large file, then this will take a while, this DVC add, because again, the file is being quote unquote copied. Okay, and then just like Git, DVC is going to tell you what next steps potentially to take. So basically, it says, okay, now do git add data csv.dvc and data.gitignore. Okay, I'm happy to do that, but maybe let's first have a look at those files. What did it do? So if I look at my data directory, you see that now I don't have one file, I have two files. I've got my original data.csv and I've got a DVC file. So the DVC file is the metadata for this file. Let's just have a look at it. And as you can see, oops, I did something stupid. Less with double S is usually more successful. So as you can see, there is a bit of information here. So what is quite important, of course, is this MD5 key, because that's basically making sure that this is the metadata for the CSV file as it is right now. So basically, that's the important one. So this is the identifier. We have the size, we have the hashing algorithm, which is MD5, and we have the path to the actual data, which is DVC, which is CSV in this case. So it's just a bit of metadata. Don't edit this by hand. That would be very counterproductive. If you want it to stop working, then change something here and you're going to be unhappy. Okay, however, something more happened. Let me do a -A. And as you can see, there is also a gitignore. We already knew that because DVC told us, but let's have a look what is there. And I'm pretty sure you can guess what's there. That is going to be the actual data file. So data.csv is going to be ignored by Git. Its metadata, so data.csv.dvc, is going to be part of the repository. So that's going to be part of your project's history if you want to view version control like that. Okay, so cool. And let me go back to what DVC told me to do. So basically, I can execute just this command. I can copy paste it if I want, but it says, well, okay, to enable auto staging, run this command. So this is DVC config. So basically, it is going to auto stage. So when I did the DVC init, you noticed that its artifacts, which needed to be under version control, were actually staged. I didn't have to do that myself. DVC did it. So DVC can do the same when I add something. It can also automatically stage all the relevant files. So that, of course, is quite convenient, and I do want to switch it on. Only I don't want to switch it on right now. I'll switch it on after I did a manual commit, because otherwise I'm mixing up commits. My commits are no longer atomic, and my obsessive compulsive me then starts complaining. Okay, so I git add this, git status, you see nothing untoward, git commit, add CSV data file, whatever. Okay, now I like the auto commit thing, so okay, I'll also execute the DVC config. Okay, git status, and as you can see, that just modified. It added something, a few lines to my where is it, DVC config file. Yeah, no surprise there. So okay, I'm happy with that. So git commit. All right, great. I forgot the -a flag. All right, now it works. Okay, so great. Now we actually have our first data file under DVC control. So that's rather cute. And basically, this is where we are. I showed you all of this. So basically, that works quite conveniently. Right. So now, how do I interact with the remote? Well, this will feel very familiar. So basically, how do we interact with the Git remote? You do a pull, you do a push. Okay, same for DVC. So basically, I can now push my data to the remote. Okay, so oops, DVC push. Okay, so now my data is not only cached, it's now also in the remote. We can have a look at our remote. Remember, it's still the local directory, so it should be here. And you see that indeed there now is a new directory files. We can have a look at it. And you see that then we get MD5. So if we look at MD5, then you see we get DC. So basically, if this is a pretty, how shall I say, a pretty populated repository, then you will see many of those two-letter directories, and they have to do with the MD5 hashes for the data, etc., etc. Basically, we have the 64 hash here. So this would be a file, and if we look at it, you see that it is actually just our original file. Okay. So yes, it's in the remote, and happily it seems to be preserved in the remote, so that's cool. Okay. So the usual things apply. So a pull and a push. Maybe it's a good idea to do a pull before you do a push, etc., etc. The usual Git sanitation things still apply, of course. So basically, that is something, yeah, pretty straightforward. Now, when I did add the data, you saw that something was happening. There was this progress bar that for a small file just flashed by, but basically some stuff happened. What happened? Well, that data was also cached. Where is it cached? It's cached in my home directory. Sorry, that's not cached in my home directory. That's cached in the .dvc directory of your project. Okay, that's something that you may or may not like, because that means that the data is also local. That means if it's large, this is also going to be fairly large. So this is something to be aware of, that your .dvc directory and explicitly the cache subdirectory might grow pretty large. So depending on where this project lives, on which file system this project lives, this will add up to your quota. So just something to remember. There is a warning sign there, so that's for a reason. Okay, so now you modify data. Okay, so basically that means if you change your data, there is not going to be a change from the perspective of a Git. Why? Because my data file is in .gitignore. So Git doesn't care about my data file. So let me just edit it. Okay, let's make this -1. Okay, Git status. Nothing changes. Why would it? It's in gitignore, so nothing changed from Git's perspective. Okay, so now, just like we do Git status to see what's going on, we can do DVC status. So if I do DVC status, you see that indeed I get a modified file, data.cvs is indeed changed. Okay, so great. That works similar to what you do with Git. So that means that now we have to add that change. So again, we're just going to add the file. If I think about adding, I automatically start typing Git, so that my brain seems to work backwards somehow, but okay. DVC add data CSV. Okay. Again, you see a quick caching step. Okay. So let's do DVC status. Okay, everything's clean, right? From the perspective of DVC, I'm done. So let's do Git status. And now you see that indeed stuff has happened. And of course, what has changed now is, of course, my metadata of my data file. Pretty obvious. I don't think there's a surprise. Notice that now, indeed, that file has been staged automatically. Remember, I fiddled with configuration of DVC, so now I don't have to add it manually. Okay, so I just need to commit. Fix data file. I don't know whether you ever fix data files, but okay, let's assume that this was a fix. Okay, so now everything is in sync, everything is clean. My DVC my DVC cache is okay, and my GitHub repository is clean. So basically, the only thing I need to do is to do a push to DVC, to my remote. Okay, And now let's again have a look at the data directory, what it looks like. So as you can see, now we have two such short directory names. We have C3 and DC. So in DC, we know what's there. That's our original CSV file. So most likely in C3 or whatever it is, we've got our new version of the file. Oops. Okay. And indeed, that's our new version. There is a -1 there. Okay. So we have our different versions of our data stored, and we can now manage those using the data, using the metadata. Okay, that was easy. Now, this is nice. We can update our data, add it, push it, etc., etc. But of course, yeah, the point is that we actually want an old version of the data back in order to rerun an experiment or to whatever. So basically, how do we do that? Well, essentially, everything is managed using Git. So Git log is going to be our friend. Git log is going to give us the commits which are relevant here. Okay, so personally, I very much like one line because then you get a compact representation of your Git log, which makes it easier to search than the long form. Let me just show you the difference. If I just do a Git log, yeah, that's pretty verbose. If I have to find my way around this, this is not so easy. And most of the information I frankly really don't care about. So if I add one line, I get this formatted in a much clearer way. I just get the commit ID, short version, and I get the commit message, and that's it, no noise. Okay, so you might use the convention that if you do a commit which is specific for DVC, so basically adding data, changing data, whatever, that you prefix your commit message with a certain default prefix like DVC column something something. The advantage of that is that then immediately, of course, in your Git log file, your data changes will stand out. So if you have a proper commit hygiene and also proper log message hygiene, then basically your life will be a lot easier. So if I would do it the way I'm doing it now, then it gets a little bit tedious because it's still reasonable, because this probably tells me that this is about the original data file. Add CSV data file, yeah, that sounds like something with data. Here, fixed data file, that sounds like something with data. So basically, I can still figure it out, but imagine that this is an active repository in which there are also quite a lot of commits that have nothing to do with your data, that have only to do with development of code. Then this gets really, really tedious, really, really fast. So having some convention to recognize commits that only pertain to data would be a good practice. Anyway, didn't do that, but nevertheless. Right, so basically, if I want to restore the data to the original, then of course this is going to be my relevant commit here, this guy. Okay, this would be the relevant commit for the second version of it, when I replace the 7 by the -1, whatever. So basically these are my relevant commits. Okay, so what can I do? I can just check out that entire commit. Easy. Git checkout and the number. So that would be in our case, yeah, wait, I need to copy this before I remove it. Okay, so if I were to do this, then indeed my metadata would be reverted to the state it was in for the original file. Because remember, this is a Git operation. I'm not doing anything to data, I'm only manipulating metadata. Okay, this may or may not be what I want. Because what is going to happen now? Well, the repository in its entirety is going to be reverted to the state it was in at that point in time. So my configuration files, my source code, etc., etc. It's possible that I want to do that. It's also possible that I don't want to do that and only want the data file to be reverted. So those are two distinct use cases. Each are very valid. It only depends on what you want to do. So in this case, I'm reverting the whole lot. Okay, so that is quite useful if I just want to reproduce an experiment also with the software version as it existed at that point in time. No problem. Okay, so let's do that. Okay, and basically now it's if you're not an experienced Git user, now you're starting to panic because you're in a detached head state and what is that? Well, basically no worries. The only thing that happens is that that now I'm at this particular commit, and basically that is what is happening here. I'll get back to safety later on. Okay, so let's have a look at my data file. And of course, you already know that's not going to be changed. It's still the -1 version, because the only thing that happened is an operation on the metadata. So this guy here is indeed back to the old one. I'm sure that you recognize the MD, that you remember the original thingy here. So basically, this is back to its original version now. Okay, so how do I get the data? Well, I can now do a DVC checkout. Okay, you see that stuff happens. So let's have a look again at our data file. Oh, magic. Now it's back here. Okay. So it's a two-step thing, which is fairly obvious that it has to be. You use Git in order to move back in time, and you use DVC checkout in order to synchronize the data. Because nothing happened to your data is not in Git, Git doesn't know, Git doesn't care. The only thing Git provides is the correct version of the metadata, or alternatively, the version of the data you want, which may not be the correct one, but okay, whatever. That's a different discussion. So basically, as you can see, I have my data as it was at this point in time. Okay, great. So now I can run some experiment, whatever. So basic, that is quite clear. Now, as you can see, I can do, maybe it's shown, is it shown? Yeah, so what is useful to notice, and I didn't point it out at that point, but basically you have also that data is now modified according to DVC. So basically that means that if I want this to stay, that I'd have to commit again. Well, I'd have to add it again and then commit the metadata. So quite logical, I'd say, but just something to note. So from the perspective of DVC, now things have changed a bit. Okay, so basically, I want to go back to the original state, and I can just go to head again. So basically to my master branch or my main branch, I think it is here. So git switch simplified to the previous branch, and I'm back again. So as you can see now, I'm no longer in a detached head state. I'm here. Let's have a look at the data file. That should, of course, be unchanged. And it is. That's no surprise. Let's check the metadata file. And that now, again, is the most recent one, let's put it that way. Or in other words, the one for which head in main is the current version. Because I'm back to head name, so yeah. Okay, so now, of course, I would need to do another git checkout in order to get the proper version of the data file again. Why do I always type git when I think faster than I type? That's a problem. Checkout. Stuff happens, and we're back to our file as it is at this point in time. Okay. So basically, don't forget this VC checkout, because that's the only thing which is going to synchronize metadata and data. Only metadata is changed by a git checkout, whatever we store, whatever you're using as operation. So don't forget to do the DVC checkout, or you're still using the old data file. Okay. So what you might want to do is not revert everything in your repository, but only revert the data file. For instance, you've done a couple of experiments. You have meanwhile noticed that there's bugs in your software. You have fixed these bugs, so many things have changed. Many things have changed in your GitHub repository, but you want to rerun an old experiment, old being an experiment with older data, but with the current version of your software. So that is, in a way, a more likely scenario, even. So if you want to do that, no problem. Again, you can use git log, but in this case, you limit yourself just to the changes that pertain to the data metadata file. So basically, I'll only get log messages, in this case, that have to do with changes in the metadata file. So just to show you what happened, let me do that. And then, oops, what did I do? Unrecognizable argument dash online. No, one line would be better. Okay, and then you see, indeed, I just get the two commit messages which are there. And of course, this is something that in theory you can also apply in general. So basically, if your data is stored in a single directory, yeah, then I can get the relevant commits for this also just by checking for this data directory. In this case, I get 2 times the same output, obviously, because there's only a single data file. But if I had multiple data files, and they would have been committed one by one, which is not a bad thing to do, then if I just list all the log messages that only pertain to the data directory, I'll get all the relevant and only the relevant commit messages for all the files in that directory. So hopefully all the data transactions. Okay, so yeah, that's just a small trick, which might also make your life easier if you don't want to go for the prefix thing in the commit message. Anyway, what you can do is, in that case, I only want to restore, in a way, the data file. That's all I want. So the safest way of doing that is just create a branch based on the current branch. So that's with git switch -c, which creates the branch, and then I've got a new branch called experiment. And then, of course, I can restore a single file from the commit I want, and I can commit that even if I want, whatever, and I can do a DVC checkout. So let's simulate this a little bit. Wait, can I do that? Yeah, I can do the workflow a little bit. So let's say I add some code. That will do. This is wishful thinking. Anyway, so now I have a commit, which I don't want to undo, because yeah, my script is now here. I can pre-process my data with it, etc., etc. So if I now would have to go back to a previous version of my data file, it would be unpleasant because I wouldn't have my script, or it would be the wrong version. So okay, I can just switch to a new branch. I create the branch. Let's call it experiment to stick with the slides. Okay. So essentially nothing changed except that I have a new branch, right? So now I can git restore. Source is, yeah, okay, I need to know my commit. So git log one line. What was it? Data. Okay. And I want to go back to this version because I'm here now. So just to show you that it works, I'll take that one. So git restore -- source is my commit. And what I want is, okay. All right. So let's do a git status. As you can see, yeah, of course, my metadata file has changed. Yeah, bloody obvious. I just replaced it by the one from previous commit. So of course it changed. It's exactly what I did. So now, if I care about this, then I need to commit. So let's assume I care about this experiment. So basically, I'm going to commit this. Okay, revert to old or original data. Okay. So now my repository is clean. And of course, what I should not forget to do is the DVC checkout, because otherwise I've got no data. Well, yeah, I have bad data. So let's have a look. Okay, there. Oh, sorry. I don't want to see the metadata file. I want to see the original data file. Okay, and it's indeed back to the version with 7. So yeah, it's again my data file. And now, of course, the advantage is I've got my pre-processing script here because the hello.py is actually still there. So I can pre-process my old data using my new script or updated script or fixed script, whatever you want to do. Okay, now depending on how this experiment runs, what you want to do with it, etc., etc., you can potentially merge that back into main or whatever, or you can just throw it away entirely. That's totally up to you. So let me switch back to the previous branch, so to main essentially. Okay, and now, of course, I don't care about this branch, so this was just a quick experiment, so I'm going to delete it. The capital D forces, because I've not pushed that to the remote, so Git is not letting me do that without first merging or pushing. So basically, I force it, and that was experiment. Okay, so there it goes. gone forever. Well, no, not really gone forever, but basically seemingly gone forever. Okay, and of course now I'm back to the original state, except of course that I should really remember to do a DVC checkout, because I still have my old data file. Okay, so DVC checkout. And there we go. And lo and behold, and there it is. Okay. So two scenarios: either revert to some point in time, period, everything, or retain whatever you have and move the data back in time by restoring from a certain, well, with a commit as a certain source. And of course, what I've shown you is for a single data file, but of course you can happily do that for any data files you have in your under DVC control. Major pitfall: forgetting to do a DVC checkout in any of these stages. If you forget, you're really screwing up, and you're going to be the same. So yeah, you really have to remember. Okay, so let's see where we are. I think we're more or less done with data versioning, but let's see. Okay, yeah, these are just some caveats. So basically, what you can do is copy data from repositories into your current repository. So basically, if you have a project, then you can actually list the data which is there. You just specify the Git URL, either a Git URL or an HTTPS, depending on which protocol you're using, etc. You can recursively list. Okay, I'm not entirely sure that should not be capital R, because capital T seems really suspicious, but who knows? I don't have sufficient memory capacity in order to remember this. So basically, let's do help. Let's see. Yeah, I already told that should have been a capital R. But the T also does the thing, then it will display a tree. So yeah. So okay, it's a little bit confusingly formulated, but the T would probably do the job as well. Well, it would do the job, but just a little bit different than it's formulated. Okay, so then you can import the data set from a Git repository. That's easy. And you can also copy files from that repository. So basically, this would be a specific file which I copy. So essentially, this is for data reuse. So once you have a Git repository with that data, you can reuse that in other repositories. How does it work? Because that's weird. I'm interacting with a Git repository and hey, wait, my data isn't there. How can this work? Well, no, that's correct. Your data is not there, but your metadata is. So if you have a remote in your metadata files, which happens to be accessible, then of course DVC reads that and it knows where to fetch the data, because that's part of your metadata of your file. So that's how that works. It works via the metadata as you would likely expect. Okay, so yeah, that's basically how that works. And that brings us to pipelines. But first, are there any questions? And second, we're going to have a break. So first questions, are there any at this point? Not really, also not online. Okay, then let's have a break. So, what is the exact time? I think it's 10:30-ish. Okay, 6-ish. So let's make that a sort of 5-minute break. Okay, if you have a question which you want to just ask verbally, then feel free to activate your microphone, because I'm guessing that's your intent.
Yes, hi.
Yeah, we put 2 questions in the chat, but we were not fast enough to type.
Oh. Mhm. Unfortunately, I have difficulty hearing you. I'm going to try to, no, just a second. I'm going to try to increase my volume, which may or may not help. I always have trouble in this room. Yeah, it's already maximum.
Could be on my end. No, there are
Let me
two
see whether I can
new.
change it here.
I,
Likely, yes, but gods may know how to do that. Left, right, that sounds promising. Audio plus sounds promising. Okay, I can't get it louder. So can you repeat your question?
there are 2 new questions in the chat.
Oh. Okay, thanks for notifying me because apparently I missed those. Yeah, okay. Yeah. Right, let's have a look at the questions. With metadata, you're forced to keep your, well, no, you're not forced to keep your data remote, but if you want to import or list, well, listing your data you can always do, but if you want to import or copy your data, that data has to be accessible. So essentially, if my data lives just in a local directory on my laptop, there is no way in this universe that I can access it from the HPC system. So if I want to list data which is in this repository, suppose I push it to GitHub, nice, to remove tool will be up to date. Great, I go to the HPC system, I can list the data, but I can't retrieve it because it's in a local directory on my laptop. How on earth can the HPC system get there? It can't. So yeah, I can list stuff under any circumstance. That's not a problem, but I can't access it. That's just not possible. So that's why if I use a local directory as a remote, this is not going to fly. However, if I were to use an SFTP, an SSH remote, and have access to that system, then I can retrieve the data. If the file permissions are right, etc., etc. All different kettle of fish, but then it is possible. If it's just in a local directory, it's simply by construction, fortunately, not possible. Because if I were to push this, then you could suddenly get files from my computer. No, I don't think so. So you see that that won't happen, shouldn't happen, and that I would be extremely unhappy when that would happen. So local remotes, fine, but no data sharing. Remotes, SFTP, S3, whatever you choose, that will work for sharing, given that the other party has the correct permissions. Okay, can containers or packages? Yep. Yeah.
Is the break intended to be?
No, not 12:30. That's maybe a bit too much. I'm going to erase it anyway because we're now running into the break, so I'll have to rewrite this. But indeed, 12:30 for the break is very generous. I'm not going to be that generous, I'm afraid. Okay, how do I wipe this stupid thing? Like this, I think. Okay, so I'll put a new one when I've answered the question. But yes, thank you, because that would be counterproductive. Okay, can container or package registries from GitLab or GitHub be used as remote storage? Never tried, but I think there are size restrictions as well. So I think you will run into the same issues at some point, but I'm not sure. No idea. So container, well, it's to say, if you have something like, what's the name of that thing? Artifactory or something like that, then the answer might be yes, but I'd have to check the documentation. But then, of course, it's something that's under your control or that you pay for. So that might be an option. But whether Artifactory or similar is directly supported, I don't know. if you're asking whether Docker Hub could be used as a remote, the answer is no, that's not possible. So it depends. Repositories to store binary data are likely to be supported. All of them maybe not, but something like Artifactory I could imagine is supported. But again, check the documentation. Yeah, but the idea is indeed to store your large data just as you store a Git repository in one place, sort of. If you use GitHub, you can kind of consider that it's in one place and that you get multiple copies on different places. Okay, clones, if I use the right terminology. So basically, yes, you store your large data in one place, which is hopefully accessible from any endpoint that is of interest to you. Your laptop, your department server, an HPC system abroad, whatever. So that's essentially what you would like to achieve. Yeah, correct. You would have to check documentation. Whether SharePoint can be used, you would really have to check the documentation. I don't know offhand. Things like Azure storage, I'm quite sure will be supported. Whether you can use SharePoint directly, I don't know. It's a bit of a business thing, so okay. I don't know whether that matches with data storage. And also typically, I'm not sure that your SharePoint manager is going to be extremely happy if you store very large data sets there. But that's local policies. I don't know.
I think if you do so, it gets indexed, no? Data.
By SharePoint.
Yeah.
Probably, I really don't know anything about SharePoint, to be honest. I try to keep it that way. Sorry?
Which might be expensive.
Yeah, it is going to be expensive anyway, because then you are storing it on-prem, typically, which is expensive. And indeed, operation-wise, I don't know even. I've never, ever looked at the SharePoint backend. It's not an HPC thing, so basically, I don't know anything about it, to be honest. So I'm not going to, you would really have to, so the list of, let's go to the list of remotes, just to show you that it's quite accessible. I had the link somewhere. So I'll just display it. It would be this guy here. Whoop. Let me share my screen again, because that is currently not the case. Yeah, I accept all cookies as usual. And I need to, yeah, of course it has, what has it done? Okay, this I need full screen. Window management hassles. Okay. All right, so basically, this is the list of the remotes. And as you can see, there is quite a lot actually. So you see Amazon S3, but this is only here Azure, as I mentioned, that's an obvious one, Google Cloud, etc., etc. But there are quite a number, there is quite an impressive list at the end of the day. I can't find it right now, but basically it's somewhere in the documentation. So the usual suspects will actually work, and whether the one you intend to use or would prefer to use is there, just check. That's the simplest answer. Okay. Any more questions at this point? I don't think so. So let's set a more, let's say, reasonable time for the break. 12:30 was a bit over the top. So, come on. I don't know. I even don't know how I got to the 30. So, yeah. Okay, there we are. So by now it is 35, I think. No, that can't be. Wait. Switch glasses. 47. Okay, so let's make that 10:55. That gives you a short 10 minutes. Okay. So for the people in the room, you are welcome to use the coffee machine. If you leave the room, you turn left, you keep on going, you run into them. They dispense paper cups, so you can use those. If you want a soft drink or water or anything, again, leave the room, turn left, and then turn right before you enter the cafeteria. There's some vending machines for soft drinks and so on. So feel free to help yourself, and I'll see you in a couple of minutes while I do some administration. Yeah.
Excuse me.
Mm-hmm.
Are you a team of HPC?
Yes.
Like I recently have a problem with MATLAB.
With MATLAB?
Yeah.
Okay. I'd say contact the help desk.
Yeah.
I'm not a MATLAB person.
Okay.
But what is your problem?
It says it's some library was missed.
Okay. Then again, contact the help desk.
Okay. Yeah.
Because they will have to check the installation. Probably something is indeed missing, and they'd have to correct that.
Okay. Thanks.
But it's best to just send an email to.
I already sent them yesterday.
Okay, yeah, but it will take a while to do that. So please have some patience.
Yeah, it's fine.
Yeah.
And do you recommend me to visit them in person?
The help desk? No, please don't.
There's no physical office.
No.
Okay.
Unless there is a very good reason to.
Okay.
But for problems like this, no.
Yeah.
No, please don't. It's just a
fine.
ticket.
And also, a quick question. Maybe it's also related to your first question you just answered. If I have data on the local, my PC, let's say, and I want to run the code on HPC on server, it is possible to do with DVC.
Yeah. Then you would have to set a remote. Your data would, at the end of the day, the data repository, data remote would be the HPC system, and you can put your data there. So you can obviously access it from the HPC system, and if it's an SSH remote, you can also access it from your laptop. So that's basically the idea.
Yeah, I mean, like, let's say if the data is super large, and uploading to HPC takes a lot of time.
Yeah,
so
it needs to get there anyway. I mean, it's not going to get there by magic. Any tool will require time to upload it, and it will be the exact same time. So there's no way around that. It's not as if magically it appears.
HPC.
Yeah, because the problem is that it has to get there anyway.
Okay.
That's for sure. I mean, it needs to be there physically at some point.
Yeah.
So in that case, it would be a good idea to have your remote being the HPC system using SSH as a protocol. And that means that you can access it from your laptop, but that the remote and hence the data repository, if you want, is located on the HPC system. And then, of course, you can use the same remote from your laptop and from the HPC system, and everything works transparently.
There's between my local and HPC, there's always authentication from GitHub, right?
Yeah, but the point is, of course, Well, it depends on how you work. So basically, this will work without any issues if you use, for instance, WSL. If you're on Windows, if you use WSL, then you can simply run an agent. So you authenticate using SSH. You just make an SSH connection to the login node. It's going to display a URL. You click that URL. You go to the authentication page. You get access through the firewall. You get a certificate. And that certificate is used in your SSH agent for all subsequent operations to those hosts. And that happens to be the right certificate in order to do file transfers.
Okay.
And the lifetime of that certificate is, I don't know, I think it's 16 hours or something. So basically for the next 16 hours, you can do data transfers.
Ah, okay.
That's no problem. Yeah.
See.
And even if a data transfer is initiated and it wouldn't finish in 16 hours, even then it just continues. It's just for new connections that you'd have to authenticate again.
Okay.
But using an SSH agent is the ideal way of doing this.
How this process works is like you have metadata on the server, and you got the data in the local.
Yeah, but the metadata is in your repository. So basically, you have a repository, for instance, in K11 GitLab, whatever. You have a clone of that on your laptop. You have a clone of that on the HPC system. The metadata is in your GitHub repository or in your GitLab repository. So basically, it's always in sync. If you do the right push and pulls and commits, etc., your metadata is always going to be in sync between your laptop and the HPC system automatically. Well, automatically, no, you have to do it, but it's the usual workflow.
Okay. Yeah, I mean, like, let's say now we submit the job.
Yes.
And it's gonna run it, and the server will fetch data from your local. Is that right? And the fetch processing was doing once, or it was like fetching it at the disk in the real time.
So the problem is if you do your data transfer as part of your job, you have to be careful with hold time because it might in some moments in time take longer than in other moments of time. So that is a little bit risky. So what I would say is if you want to stage your data using a job, so non-interactively, I would suggest that you have a job with dependencies. So the first job is going to stage the data. It's going to do a DVC pull. And the second job will only start when the first job ends successfully. So you get the dependency chain. And then, of course, you're sure that when your computation job starts, that the previous job, which did the DVC pull, actually completed successfully.
Okay.
And that means that you can put some limit, some hold time limit for the transfer, which can be very generous. And you also just need a single core, so basically that's a very small job. If it takes long, no problems, it will start soon anyway. And you are sure that your data is transferred at the moment your computation starts. And that you are, if you do things right, working on the correct data set.
Okay. Yeah. Thank you.
Yep.
Sorry, just a quick practical question. For the attendance in classroom, should we also connect to have register?
I'll circulate this so that you can just, if you just write down your name, the important thing to identify you is that I can make a connection between your name and your email address. So you're likely all KU Leuven, so that's quite easy. If you just write down your first name and last name, I'm fine. Then I can map it to your email address. So if you please write down your name. Okay, I'm going to extend the break with a minute to get a one shot of coffee. So, right. Okay, so the part before the break was just about data management, and that's of course an important part of operations. So that's already good, but we can go further. We can go significantly further by actually formalizing our pipelines. So basically, typically, an experiment consists of multiple stages. One stage should precede the next. Some stages can depend on multiple previous stages, and so on. So basically, we can have rather convoluted networks, convoluted workflows at the end of the day. Did everyone write down their name? No. Okay, so, and that of course is also something that may jeopardize reproducibility. Because of course you can do that happily with a series of scripts that you execute, and maybe you have a meta script that executes those scripts, etc., etc. But still, reproducing this is error prone and potentially problematic. So if we can improve that process, then of course that helps us with respect to reproducibility, and it also makes our experiments more easy. There are a billion ways of doing that. So for instance, in the training on workflows on HPC, I've talked about Nextflow in order to formalize workflows and execute them in a consistent and reproducible way. So that is one way of doing that. This is a different one. Just like there are many alternatives to Nextflow, this in fact is one of them. So this is just an alternative to that. Okay, of course the approach, the philosophy is always the same. You think in a structured way about your experiment, about stages, the various stages in your experiment. What could that be? For instance, that could be pre-processing. You get your raw data, and that needs to be pre-processed somehow. For instance, you might need to deal with missing data. You might want to sanitize your data or to validate your data? Are the values in ranges you expect, etc., etc.? So all these steps are very important, and especially in machine learning, they're pretty crucial, typically in data science in general. So they're pretty critical. But in a way, they're also, you have similar things in other domains, because, for instance, suppose that you do a simulation, and that simulation starts from a configuration file. It might not be a bad idea to validate that configuration file before you start the actual simulation, because your simulation is going to be expensive. If it crashes half through because the configuration value was out of range, then yeah, you're going to be unhappy, and the taxpayer will sympathize by being also unhappy. So basically, validation, data validation, and so on is an important step in typical experiments. So then you run your experiment, whatever that might be, that again might consist of multiple stages. So basically, for instance, it could be, let's return to machine learning context, that you do some training of some model. Okay, you might even train multiple versions depending on what you're doing. And then, of course, that's nice, you have a trained model, but then you want to validate the results. So there is a testing stage afterwards in which you use your model in inference mode or whatever. And then there might be finally a data aggregation step where you combine the data produced by multiple runs in your experiment or whatever. So as you can see, it's rather trivial to come up with a, well, okay, sort of straightforward, but not quite straightforward pipeline. Okay, so if we can get some support for that, that might be useful. And indeed, data version control, DVC, is going to help you there. Okay, so I've already used the terminology. So basically, in DVC speak, a single step, an atomic step in your pipeline or workflow, if you want to use different terminology, DVC use pipeline, then that would be a stage. So that means that a trivial pipeline contains a single stage. Not very exciting, but typically you have multiple stages. And there is a question in the chat. I'm likely not sharing my screen even before I switch to the chat, and notice that someone is mentioning that I'm not sharing the screen. I'm going to do that, and then verify whether my hypothesis was correct. And indeed, my hypothesis was correct. And I should start doing a stint as a clairvoyant and increase my income a bit, but okay, whatever. So basically, you didn't miss anything because I just switched to this slide, so no worries online. So basically, as I mentioned, terminology is pipelines. That's a workflow. Parts of your, or things that happen in your workflow are stages. That's essentially what you've got. So in order to do this in a structured way, that of course means that you need to specify the dependencies for one stage with respect to the others. So that means that the output of those stages should be the input of the next stages, etc., etc. So that's how you connect the thing, which means that you get a network at the end of the day, or a graph in mathematical terms. So you are in fact constructing a graph of steps. So that's one thing which you need to take care of. Each stage also has parameters. For instance, suppose, again, machine learning, that you are in the training stage. No, you're not in the training stage, you're in the pre-processing stage. One of the parameters could be, okay, split my data set into a training set, a validation set, a test set. Okay, so a parameter would be, okay, what's the fraction of my entire data set that I'm going to use as a training set, etc. So basically, these are parameters of a stage. So that's also quite important, and it's also something that, in a way, you should keep track of, because that's not part of your script. That's not part of your pipeline. That's metadata to the execution of your pipeline. So that's a part of an experiment. But okay. So basically, we need these parameters, typically. Sometimes we don't. Depends on what you're doing. For instance, if you have a stage that just validates the data, it's not likely that it has many parameters. It could have some, but yeah, unlikely. If your stage is training a certain model, yeah, then of course all the hyperparameters are likely to be parameters of that stage. So depending on what the stage actually does, what its payload is, you will have 0 to very many parameters. But it's something we're interested in because we want to reproduce. So how can we do that? And then, of course, certain steps, certain stages in your workflow may produce metrics. For instance, if, again, say machine learning, if I'm training, then I might want to keep track of the evolution of my errors, for instance, or of my loss function, things like that. If I'm doing a simulation, I might want to keep track of some convergence criterion, how that evolves. So typical stages where things really start to matter do produce metrics under some form. So again, that's optional because, yeah, in your data split stage, there's nothing much metric on, so yeah, whatever. But for instance, in the pre-processing step, you might be interested to know how many missing values there were, how many imputations were done, or what the range of certain variables is, etc., etc. So you can imagine many use cases for actually having metrics which you want to consult later on. So that can be part of a stage as well. So dependency is input, and then of course a stage produces something at the end of the day. Otherwise, yeah, you're kind of not doing anything. If you don't produce anything, nothing has happened, except an expensive use of energy and taxpayers' money. So basically, every stage is going to output something. And then, of course, you need to define what is going to happen in that stage, and that can be many things. So, for instance, that can be a Python script, that can be an R script, that can be a Bash script. Essentially, it can more or less be what you want it to be. So that gives you quite a lot of liberty in order to translate your typical workflow into a data pipeline. And of course, what is connecting the various stages are dependencies on the input part and outputs on the output part. So you match an output of a stage to a dependency of the next stage in that pipeline. Okay, so the pipeline itself is going to be a graph. And of course, it's going to be a directed graph. That's pretty clear, because a stage precedes another stage. So that implies direction. So that is going to be mathematically a directed graph. And for DVC, it should be an acyclic graph. So you cannot have a cycle in your pipeline. There are easy reasons for that. Basically, that eliminates infinities. You can't get an infinite loop if you don't have loops in the first place. Okay, so that is the major reason why in many workflow systems, not necessarily all of them, but in many workflow systems, cycles are not allowed because yeah, that can go out of hand and everyone's going to be unhappy, including you. So basically, that's why typically that's excluded. Is that a limitation? Sometimes a little bit. But then basically, if you need a cycle, you would have to do it in a single stage or cheat a bit or whatever. There are always options to get around things, but mathematically, that's what it should be. Okay, what you also hope for from a workflow system is that if you've done something already and there is no reason to redo it, that it doesn't get redone. So basically, that I can resume from where I left off. For instance, suppose that I'm training a network and then later on I'm testing it. Okay, so my entire pipeline also is about data pre-processing, right? So I run an experiment in which I pre-process my data. It's not done before, so I need to do it. I run a training stage, I run a validation stage or a testing stage, whatever. And then I decide, okay, let's redo this experiment, but let's change the hyperparameters for the training stage. Okay, great. So I I change my parameters, I re-execute my pipeline. Why would I do the data pre-processing? The data hasn't changed. Why would I bother? So that is done automatically by DVC or taken care of by DVC, that stages that need not be redone will not be redone. Another reason why directed acyclic graphs are nice, because it's easy to know what you need to redo. If you cycles, yeah, good luck with that. Okay, so how do we do that? And this I'm really not going to do hands-on. This is adding a single stage. I mean, I'm not going to type this. No way. So sorry about that. This is not going to be interactive. It's a lot of stuff, but if you look at it step by step, it's actually not that horrible. So DVC, that's predictable. Stage, that's a subcommand. So now we're talking about stages. And add. I want to add a new stage in my pipeline. Okay. And then I get dash name, the name of this particular stage. So in this case, it's split data. You can already guess what I'm doing here. I'm going to split my data set into, I don't know, 2 or 3 parts. Don't remember what I'm doing here. Doesn't matter. But basically, this is a pre-processing step. Okay, so I need to indicate what it depends on. And that will be on my original data file. So the data CSV here. And then it will also depend on the Python script, which is going to do the processing. So this is kind of nice, because that means that if you remember what I said about redoing pipelines, suppose that I don't change my data set, but I do change my script in order to split the data, and that script is a dependency, then of course there's a very good reason to redo that stage. So it's nice that you can also add scripts to your dependencies of your stages. So if you look at which script it is, basically it's in the source directory split data.py. Okay, and indeed that is exactly the script which is executed somewhere here, source split data.py. And I can even be a bit more careful, a bit more accurate, and also note that in fact that script split data, in fact under the hood uses a Python module. In this case, utils.py, which is also in the source directory. So I fix all my dependencies, not only with respect to the data which I'm going to process, but also with the tools I'm using to actually process that data. Okay. So essentially, one of the dependencies could be an environment definition file of your Conda environment, for instance. And then stage could be install that Conda environment. Or similar for an obtainer image, the recipe could be a dependency. And the output, an obtainer image. And if the recipe changes, the obtainer image changes. I mean, you have quite a lot of liberty here. And that means that it's part of your data which goes into your experiment management system, because that's where you're going to be. Okay, so that's the dependencies. In this case, 3 dependencies. And then you can specify parameters. So basically, in this particular case, for split data, there is going to be a test size, and there is going to be a data size or something, no, random state, etc., etc. So those are going to be my parameters. Where are the values? The values are not here. So the values are elsewhere. I'm just specifying which parameters I need to track, not what their value is. That will also be tracked, but automatically. So this is just specifying the things that are important, not the values themselves. So that's the parameter thing here. And I can have as many parameters as I want. I just have to list them, comma separated. Okay. And then, of course, as I already mentioned, yeah, okay, here's no metrics. I mean, no one cares. We see an example of metrics later. In this case, we don't care. So the other thing which we definitely need to specify are the outputs. What does this stage produce? And as you can see, there are 2 things which it produces, a training set and a test set. So simply 2 comma-separated value files, and essentially that is going to be the output here. Okay, so this is all meta information about what should happen. What actually happens is this bash fragment. At the end of the day, this is bash if you want. So basically, I'm calling a Python script. This one, remember, that was a dependency. And that is going to use an input file. That's this guy here. That was a dependency too. And it's going to output into split data. Okay, that's just the output directory. So what it will do automatically in that output directory, it's going to create the train.csv and the test.csv. Okay, easy. Once I've done this, of course, again, some meta information will have been generated, which I need to commit using Git. So my pipeline information again goes into Git. So that is again rather neat. Remember, I've what was the name? Auto commit thing, auto staging on. So basically, I don't have to stage things. I can just immediately commit them because DVC will have already added, staged them for the next Git commit. Okay, so basically, DVC adds will create a file, and that file is just a YAML file, so essentially human readable, and that is a description of the workflow. So in this case, I'll have a trivial workflow that just contains a single stage, but as I add more stages, each time, of course, that YAML file is going to be extended with the next stages and so on until I have my entire workflow. Okay, and this should actually be DVC stage add, not DVC add. So in the stage sub command, let me add a remark here that on page slide 23. I need to fix this. Okay. All right, so that was easy. So what about parameters? As I said, I only specified which parameters were relevant for that stage, not what their values were. So where are the values? Well, the values simply live in yet another YAML file. By default, it's called params.yaml, but you can specify something different. It need not be params.yaml. It can also be JSON format, by the way, so both YAML and JSON are supported. So depending on which you prefer, you can pick one. YAML is the default, so I didn't bother to go to JSON. Okay, and what you will recognize is a split data. Okay, and then test size and train size. Sorry, not test size and train size, sorry, test size and random state. Remember how I specified that on the previous slide? There was balance, split data dot test size, split data dot random state. So this is where these values come from. Okay? So that means that I can use the same pipeline to do multiple experiments with different values of these parameters. And of course, this file goes under version control, meaning that I can reproduce the whole lot. Because I can always check which parameters I used for a certain experiment. And if I want to redo that, I can simply check out or restore with the source, and I can redo that experiment with these particular parameter files and parameter values. Okay, so basically this contains all the parameters for all the stages. You can also set a specific file per stage, but okay, let's not go there. So basically this would be the split data stage, and this would be the train model stage. And again, there is a series of parameters, in this case some hyperparameters for this particular model. Okay. So you can use those in scripts. So essentially, I can, of course, open that YAML file and use the parameters in the script so that I don't have to fiddle with them. So this is, of course, a good practice to do that. YAML is okay. I'm not entirely sure whether this is standard Python library. Can't remember offhand, but okay, it's easy to install as part of your Python environment. No problem there. Okay, so you open your file, you read the parameters, and then you can simply use them in the script which you're using. So essentially that means your script doesn't contain parameters, your data pipeline doesn't contain parameters, they're centralized into a YAML file. Question?
Yes. Would you have different parameters of YAML file per environment? Say I run something on CPU versus on GPU.
Okay.
Make two different?
So the question is, would there be two different parameter files when I either run on CPU or whether I run on GPU? It depends. In fact, in a way that has more to do with the pipeline than with the experiment. If you view parameters as parameters of your experiment. So for this particular example, I would actually say that you would have the same parameter form. Because regardless of whether I run this on GPU or on CPU, it's going to be the same thing. These are for the training stage, for the pre-processing stage, yeah, it's just for reproducibility that you specify the random state. The test size you specify because, yeah, that's what you want. And the parameters for the trained model, yeah, they are hyperparameters of whatever training algorithm I'm using. So no. On the other hand, you could say, okay, one parameter could be the size of my data set. Suppose I have, I don't know, 10 million examples. I really don't want to use all 10 million of them on my CPU because I'll be there forever. So one stage in your pipeline in that case could be, okay, random subsample my dataset for a certain amount of examples or for a certain fraction or whatever. So that could be, and then I try out my pipeline, I fiddle a little bit with my algorithm, blah, 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 I prepare things, and then I think, okay, now, given that I don't have a powerful GPU in my laptop, I want to move to HPC to do the real thing. Then, of course, I would change that parameter. But then it's a different experiment. So is that a different file? It's a different version of the file, for sure.
Well, I could imagine that during development, because you're on your laptop, you choose for a small model,
yes,
for instance, that you would replace
with a larger one.
You migrate to HPC
yeah.
with a real model.
Yeah, well, but same thing. parameters themselves, the parameter names remain the same, the values will differ. So if we make abstraction of this, then CPU or GPU is simply a different experiment. So there can be, need not be, but can be different parameter values for that. But it's not as such that it's something different for CPU and GPU, it's just another experiment. So if we lift this to a somewhat more abstract level, for me at least, it gets more clear. And essentially, my parameters are just some commit in my GitHub repository. So the parameters which I use for development on my CPU are just going to be a different commit from the values I use for the actual experiment which I do on the HPC system with GPUs. It's just a different commit. It's just a different realization or run, if you want, whatever you want to call it, of my experiment, of my pipeline. That's the idea. Okay. So it's all commits at the end of the day. Git commits, that's all there is. Okay. Yeah, so basically, I've only a single source of truth with respect to my parameters. The parameters for the pipeline and for the scripts are just in that params.yaml file. That's it. Everything's there. Okay, great. So a one-stage pipeline is pretty boring. I mean, then there's more overhead than there's gain. So basically, you will typically have multiple pipelines. So this adds the next one. And then, of course, you see the dependencies arising, because now, of course, I had outputs, test and train CSV, but those will be dependencies, so inputs, for this stage. You see them here somewhere. No, I only the training one in this particular case, sorry. And then, of course, the train preprocessor script, whatever that does, and then again, the utilities, etc., etc. So again, I mention the script as a dependency that I'm going to run here. This is apparently not the training stage, it's a preprocessing stage for whatever reason. Train, preprocess, yeah, okay. I thought this was a training stage, but it's preprocessing. Okay, so basically, in this case, we don't bother with parameters because apparently there are none for the stage, great. So we just specify the output, and then you see that the output is going to be here somewhere. So this is the output. And again, I'm just running a Python script based on the data file. I'm providing the input, producing the output for this particular stage. And again, we just need to commit that, and we're done. Okay, so again, the only thing which is going to happen is a change to that DVC YAML file. So essentially to your pipeline definition. That's all. Okay. If you want to change an existing stage, it's again DVC add, but with the --force option. If you want to remove a stage, DVC remove. In theory, you can also directly edit this DVC YAML file, which might be in some circumstances a bit easier, but yeah, okay, that's up to you whether you want to do that or not. Of course, what you shouldn't do is edit it in such a way that it becomes invalid and that you have a syntactically incorrect YAML file. Then, of course, no one is going to be very happy. Anyway, it's under version control, so what do you care? Okay, great. I mentioned metrics. So these stages here were not particularly interesting for metrics, but now we're in the I'm computing metrics for this stage, so I can also specify them here. So the metrics are going to be in this train.yaml file. Okay, and that is again going to be used. That is going to be the output of this, or one of the outputs of this training thing. So note that this stage does not have output, but it will produce metrics. So it still does produce something, only it's not an output. So this is in your DAG, this is going to be a node that essentially has no nodes after it anymore. So this is a terminal node. Okay, so again, we commit the usual thing. So at the end of the day, you end up with multiple stages, and it might be somewhat complicated. So in order to get a graphical overview, there are quite a number of ways, but one way is a dot visualization, and then you get this kind of graph here, where you see the various stages, either in terms of the stage names or in terms of the outputs. So if you do DAG out, then you get it in terms of outputs, otherwise you get it in terms of stages. But as you can see, this is already a rather convoluted example in the sense that it's non-trivial. There is data pre-processing at several stages and then etc. etc. So, okay, it's a reasonable example. If you want to see the whole lot, no problem, it's in the GitHub repository. Okay, so great, we defined our pipeline. How do we run it at the end of the day? Well, that's again quite simple. DVC repo. Okay, I always type a repo, of course, but okay, that's Git again coming up. So repro for reproduce. That's the rationale behind the name. And you can just say, okay, show me what you're going to do, but don't do it yet. So that's the dry run. So with --dry, it's going to just report what it does. And then if you just do DVC repro, it's going to do only what it needs to do. So if this is the first time you're running the pipeline, it's going to do every stage. However, if then you have a subsequent run in which you don't modify the data, no dependencies of pre-processing stages are changed, whatever, but you change, for instance, some meta parameter, some hyperparameter in your training model, then only the training and all the subsequent stages are going to be redone, but not the pre-processing. So that is the default behavior, and that's, by the way, different from Nextflow. For those of you who are familiar with that, with Nextflow you have to say, okay, be lazy. Here you have to say, do everything. So if you want everything redone, then you just add the false option here. Okay. So that is going to, again, produce a new file if you run it the first time, or update an existing file, dvc log, when you re-execute. And so basically, this file also goes under version control, and you commit it after the run. So you see everything happens in the Git repository, or is recorded in the Git repository, let's put it that way. Okay, at any time you can check the status of the pipeline, and then basically you see that this has been modified. So essentially, I should redo split data because there is a dependency that is modified, and then again here, that's the file that changed. So that's the meta file. So basically, that is why this is going to have to be redone. And now, of course, we are, with respect to reproducibility, again full cycle. Given that each and every stage, well, let's not use the word stage, that each and every state of your experiment is in Git, I can reassemble any experiment I want. I can get the version of the parameters, I can get the metrics, I can get the pipeline. If I add a stage to a pipeline, no problem. I can go back to the previous pipeline just by picking the right Git commit and starting from there. So as you can see, I can, at this point, I can reproduce anything I want, provided I use this with discipline. Okay, so that's essentially the idea. So this is really pretty powerful. Okay, great. So metrics. Yeah, if we are interested in stuff that happens, in stuff that is produced by our experiments. And so, for instance, in this particular case, I can show the metrics which were produced. So that would show me the results, well, the metrics of the most recent run. And notice that was part of my pipeline. I defined what the metrics were going to be. So basically, as you can see, I've got in this particular case, for the training and for the test, I've got the accuracy, the F1 score, the precision, the recall, etc., etc. Okay. So that would be the metrics I recorded for this particular experiment. So this was not a training process in the sense of that I'm storing as metrics the evolution during the training. This is just metrics at the end of the training. I don't remember which algorithm this was, but it was something that basically is one shot and easy. It could be something stupid like a logistic regression or something like quite. Anyway, so it's very easy to check. It's also very easy to compare metrics with the last commit. So basically, what did my changes now change compared to the previous version? So basically, oops, that sounds bad. So basically, you see that you get the metric here. So again, we have the same list of metrics: the accuracy, F1 score, etc., etc. All of these. We have them on test, we have them on training, and we get the head. So that is my last commit. The workspace, that is the current state of my working directory. And you even get, as a bonus, you get the changes. So basically, as you can see, I've got positive changes for all my metrics, given that it's nice if they increase. The current parameters, which I didn't commit yet, so this is my last run that I didn't commit yet, is actually better than the last one I did commit. Okay. So it's very easy to compare experiments. It's just trivial. You just have to say, okay, give me a diff of the metrics. Easy. Okay, comparing arbitrary runs. Again, it's just a DVC metrics diff, and you specify 2 commits. Okay. So basically, between those commits, you see that again, there was only positive evolution. So things improved from the first commit to the next, for whatever reason, which you can check, because you can, of course, then, for instance, compare the parameter files of these runs, or whatever, the source code of these runs, whatever. But basically, this helps you to very easily compare the metrics between runs. If you want to see all metrics, just do --all, and then it's easy. I said, okay, you can compare parameters. Yeah, you can compare them in different versions of the file. You can also do that quite easily with a DVC params diff. And of course has the same semantics. So basically this is going to compare the values of the parameters. And remember, I declared those explicitly, so it's easy. Compare them between the last commit and the current working directory. And basically you see that in this case, I increased train model, so the C parameter for the training model stage, I increased that from 1 to 1.5. So you will notice there are more parameters, but this only shows what changed. So that means that all other training parameters, and I think there were, for this train model thing, there were 3 parameters, if memory serves. So the 2 others are just unchanged. And again, you can compare between commits, and then you see that between these commits, it was also the C parameter that was varied, but from 0.5 to 1 in this case. If you want to see all the parameters, again, just use -- all, and it will show the whole lot, not only what changed, but all the parameters. Okay, so this is quite cool because this gives me a very easy way to, on the one hand, compare results, so metrics, of my experiments, and on the other hand, the parameters of those experiments, just by using DVC something with question.
I have a question regarding the parameters. So in some experiments, you might want to do a sweep of parameters, like what we said.
Yes.
And in my understanding here, the logic is each time you change a parameter, you comment, and then you have a version of the model with that parameter. So if you want to automate like 100 parameters sweep, can you do it? Is there automated way to do that?
So a very good question. Very often you want to do parameter sweeps. There is a parameter value that changes into a range with a certain granularity, and you actually want to compare the outcome of your experiment when you sweep over that parameter. Is that supported? The answer is yes, and we'll come to that. So indeed, that is supported, because indeed it's such an integral part of this type of workflow that DVC supports that explicitly. Yeah. Okay. Now all the examples I've given were for Python. So what if you want to use MLOps? I heard MLOps somewhere. Or what if you want to use R? For MLOps, frankly, I don't know. I would have to figure it out, no clue. But for R, it's quite simple because I can run. I don't need to actually. Sorry, wrong. Backtrack, rewind. Basically, I have not talked about R or MATLAB, but everything I talked about up to this point is in fact agnostic of which tools I'm using. Python, R, MATLAB, whatever. No one cares. Now, with the next chapter, we'll actually come into some parts where it does matter. But up to now, no problem. The only thing, there's one thing, you have to be, to make things reproducible and safe, you have to be able to read a YAML file in your favorite programming language, whatever that is. So for R, that would be quite simple. There is a package YAML, and reading a YAML file is really, really trivial. You just YAML load file, and I think actually they even stole the file, the function names from Python, but okay, that's a different thing. So basically, that would give you again a configuration object and all the. It's a list. It's an R list. So basically, you can get all the parameters here. Okay. And for MATLAB, there is likely to be something similar, but yeah. So that's the only language-specific thing there is up to now. So yeah, this is agnostic of whatever you're using. Okay, so now not anymore. Now we turn our attention to yet another level, and that's experiment management. So basically, we tune up the volume or the level of sophistication a little bit by each subsequent section. Okay, so experiment management, what do we want to do? We want to log experiments, and we want to log them much more fine-grained than we did up to now. And for that, we can use a module which is called DVC Live. So that is, as you can guess, developed by DVC. And indeed, this is Python specific. So this is Python module. If you're using R, no worries, we'll get to that. If you're using MATLAB, that's going to be interesting. Anyway, so what do you want to log when you do experiments? You want to log the parameter values. You want to log things per time step, potentially, like for instance an accuracy or validation error, something like that, whatever, or loss function, what do I know? So those you want to change. You want to also log metrics. And you may even want to log images or plots or artifacts, whatever they might be. Models? Someone? Yeah. Okay. That's nice that you can log all that, but you'd also like some reporting here because, yeah, I mean, it's easy to lose track. And again, you want to compare experiments. And preferably, you want to share all that because it's nice if I do an experiment, but if I'm part of a research group, it might be nice that my colleague can actually review that experiment and steal my parameters, for instance. Whatever. So basically, you see where this is going. I need to share this. I want to share this because I'm working in a research group. Okay, so sharing can be done entirely via your version control system, GitHub, GitLab, whatever. But there are a bit more bells and whistles if you use DVC Studio, which, as I mentioned, is a paid service. Yeah, I talked to them. I mean, I'm not sure I want to talk to them again, but yeah, okay, whatever. Let's not go there. So, how does this DVC Live thing works? So this is Python. So this would be my script. And of course, it's something very sophisticated. So I somehow start with a system which is based on some parameters. And the parameter value in this particular case is 5. This has been it's the result of a very sophisticated computation, or it's stored somewhere, whatever, I don't care, but that's the value. Okay, and then I start iterating over my system and updating it each time. So I evolve my system magically somehow, and I do that for a certain number of steps. Okay, great. I compute some metrics based on that system. What they are, I really don't care at the end of the day. And then I print those metrics because I want to keep track of how things evolve over time during this particular computation. And then, of course, at the end of the day, I want to make sure that the result of the whole evolve steps which I did is somehow persistent. So I save that, and in this particular stupid example, I'm just saying, okay, I'm going to pickle that object so that I can easily revive it in some other context. Replace this by your favorite serialization format. Okay, so that's your workflow. How does DVC Live come into that? Well, basically, the code is getting somewhat longer. So we start by importing the module. So far, it's easy. And then we do with DVC Live, we already specify the type of report we want, HTML. So this is a context manager, which is good because it means if the DVC people did their job, if this goes south, so if it crashes somewhere during this experiment, files will be closed properly, etc., etc. There will be error handling and so on. So if they did everything right, this should be really robust. And it can be since it's a context manager, so yeah. Okay, so again, I initialize my parameters, no problem, but then I also log them. So as you can see, this live object, which was created by this object creation thingy, whatever, actually has a way to log parameters. Okay, so I give the name of the parameter and value. Calling your parameter is probably not a good idea, but okay, you see where this is going. This could, for instance, be learning rate. And then you would have learning rate as a name and the value is recorded. Okay, then as usual, you initialize your system, you start running, but in each step, you're going to log the metrics. And as you can see, you name the metric. So in this case, it's again total lack of imagination. My metric is just called metric, but that could be accuracy, that could be error, whatever. And you record the value. And then you tell Live that you go to the next step. So don't forget this next step thing, because otherwise it's not aware of the passage of iterations. So it's the next step thing that makes it aware that iterations are, that you go to the next iteration, that things are new. Okay. And then at the end of the day, you log an artifact, and essentially that is my PKL file, and that is a model. Type is model, and that there are several types. Don't remember them offhand, so check the documentation. There are quite a number of useful ones. So basically, now my log, the VC live log of my experiment, is going to contain the input parameters. It's going to make a record of the artifacts produced by my algorithm. So in this case, the trained model or the evolved system, whatever you want to call it. And it's also going to keep track of all the metrics I collected during the iterations which I did in order to get to the final stage of my system. Okay. So that's basically the idea. And of course, I do not necessarily need to log every step. I can make this dependent on every 10th step or whatever granularity I want logging. So of course, that's totally up to you what you do there. Okay. Is this more or less clear what happens here? So this gives you something for a specific stage. Yeah. Question.
Maybe another maybe stupid question is, this is just a board for logging. So is there a drawback in if we use other boards like TensorBoard or Neptune or devices? Is there a drawback in integrating the logging on that, like the version control on the C, or this is something that you can do?
Okay, can you mix and match? So for instance, suppose that we are using TensorFlow for training, for instance. And as you know, if you're familiar with TensorFlow, there's this very nice TensorBoard thing on which you can monitor in real time the evolution of your parameters during the training process. So that's rather cute. Does this mean that if I want to use TensorBoard, I can't use DVC Live? No, you can combine the two, no problem. So there is no reason that you cannot combine these two. Of course, yeah, depending on what you are logging, it might start to consume time. So depending on what your metric is exactly, or how many metrics you store, yeah, and depending on how long your iterations take, so that's a consideration. But apart from that, there is no reason not to do that. Now, if you are using something like TensorFlow or Keras, typically, well, you can do two things. Either you really have an iteration over steps, or you use the framework and let it do the step management by itself. So if you do that, you would have to have a callback that actually records the metrics. But unless my memory really fails me here, for instance, Keras will offer that. You have a hook which you can specify that should be done after each epoch in your training. So that's an option to do it that way. Because you don't, typically in Keras, for instance, you don't have your iterations explicitly. You just call sort of, what is it called? Fit or whatever, and it will keep on doing epochs until maximum epoch has been reached, or you have a convergence criterion, whatever. So basically, that means there is no explicit for loop. So if you want to record the metrics using DVC Live, then of course you should provide a hook that's executed after each epoch in your training run. But that should be possible, unless I'm very much mistaken. Keras, for instance, has that. Okay. Whether that then means that actually it's either that hook or TensorBoard, okay. This I'm not going to take bets on. This I'm not sure of. So that's a matter of checking the documentation, whether you can, in that sense, combine. But if you have an explicit iteration, then of course you do whatever you like. Does that more or less answer your question? Okay. Right. So fairly straightforward, and we can collect quite some information here. So basically, you run your experiment. So basically, you run your script as usual, no problem. And it will create quite a lot of stuff. So you will get a DVC YAML file. So basically, that will contain the location of all these files. And by default, they're going to be in a directory which will be created DVC live. It will contain a number of files. So for the metrics, for the parameters, and potentially for plots for these metrics and so on. So that's basically the idea. So essentially, you will actually have sufficient information to automatically do visualizations, as you'll see in a minute. And then there is also report.html, which you can open in a browser and just inspect. Okay, so basically, that's nice, because now I can actually share my experiment just by pushing it to a remote. And then, of course, it's on GitHub, for instance, or on GitLab on-prem, and anyone with access to that repository can inspect the results of this particular experiment. That person can see the metrics, that person can see the parameters, that person can see the evolution graphically represented of metrics collected during the run of that experiment. Okay, so that is convenient. And this is really spooky. And it took me quite a while to understand what was going on under the hood. Because basically, I really couldn't get this. And that was because there was something in Git which I was missing. And that is what they're actually exploiting. That's why there is experiment ref here. So, and that's the actual thing here. So I'm not going into the technical details. For those of you who know Git quite well, they know what refs are. And basically that's what DVC uses under the hood in order to store your metadata about your experiment. And it's also that what goes to the repository. Never mind. But yeah, it took me quite a while to figure that out, because I really couldn't make sense of it. Anyway, so basically, this is what you get if you open the HTML report at the end of the day. So you get a listing of your parameters, which are here. You get metric values at the end of the day, well, at the end of the experiment, and then you see that you also get metrics evolving over the steps. So basically on the x-axis is simulation time. It's in this case a discrete model which is running. On the y-axis is the metric I've been collecting. So basically this is very much not machine learning. And I've especially taken this example in order to illustrate that this is an abstract thing. It need not be concretized for machine learning. It can be any experiment. So this would be a simulation of an easing model. So basically that's statistical mechanics, if you want. So essentially this is the evolution of such a system over time. You see that the magnetization goes approximately to 1 and then starts wiggling around. The energy drops to something, in this case negative, seems odd, but okay, that's normal, and it's wiggling around there. So this could have been computational fluid dynamics, this could have been anything you like. This is just an abstract experiment. That's it. What you do is totally up to you. It needs not have anything at all to do with machine learning. This is especially this. I took this example to drive that point home again. Okay, so experiment management. All right, I can list the experiments. That's just DVC XLS. I can list all experiments, so not only the ones which are currently at HEP, but also the other ones. and I can save the workspace as an experiment. Okay, so you see I can name experiments. I can rename experiments if I want. I can remove experiments. Okay, so every experiment I do is recorded, and they go into Git refs. That's the basic thing. Okay, great. So I can query experiments. So basically, I can just say, okay, give me for changes, and I want that in Markdown. So that's the -md here. So show me only the things that that's changed. So basically, now I'm comparing workspace with main. So main is the last commit. Workspace is what I'm currently, my last experiment, my current experiment that is not committed to main yet. Okay, and then you see indeed differences. For instance, the energy was lower with this parameter and higher if this age is higher, which is all pretty logical if you know what the thing is doing and if you know the model which is running here. So basically, that is the idea. The important point is we go from 0.5 to 1 approximately in magnetization, and that's due to this age parameter. Anyway, never mind. So basically, if you do this, the problem is that it's sent to less, so to a pager, and that is basically a little bit annoying since that will wrap by default. So if you want to make sure that less does not wrap, then you can pass the -s option. If you want that to happen automatically when a pager is called under the hood, you can do that via environment variable. So the environment variable is less. If I specify less with -S, it's not going to do what's it called wrap the lines. Line wrapping is the word I'm looking for. So basically, that's the idea of this prefix here. So it's just something useful. You can also use --JSON instead of --MD, whatever. You can use CSV or no pager, etc. And then at the end of the day, what you can also use is a very nice utility or family of utilities, which is called CSV Kit, which allows you to do all kind of processing on the fly of CSV files. So for instance, CSV cut will allow you to select columns out of a CSV file. CSV show allows you to manipulate how the output looks, etc. Sorry, not CSV view, CSV look. Okay, so basically that's the idea. And then you can also have a look at the plots. So for instance, show me the plots for the high energy or high temperature experiment, and then you get the plots. And if you are on a system that has a browser, just specify --open a browser window, and you get the HTML page immediately in that browser. Otherwise, it's just an HTML file which you can transfer and open. Okay, so this is done on the fly. These plots are created on the fly based on these TSV files, so tab separated value files, which were in, remember, DVC live / plots / something or metrics plots something. So that contained all the raw data, all the textual data to create these plots. So the plots are not stored, only the data which you need in order to create them. Okay, comparing experiments. Guess how? DVC exp diff. And then you specify 2 experiments, and you see that the metrics changed. And you also get the change. So basically you see if there is a negative change, then that's also clearly displayed. So in this case, of course, that does not mean that it's better or worse, it's just different parameters. Okay, so this is quite convenient. And then you can also see the evolution of things. So basically, you get a diff between the files as well. Okay, well, let me go back. As you can see, I get a plot for both of them, so there is a legend added automatically, so it's all pretty clear what's going on. Okay. Sharing experiments. So as I already said, this is all done using Git refs. So basically, you should do a DVC X push to origin, and note origin here is your Git origin. So this is not going to be put to the DVC remote as you might expect, as I expected when I before I understood what was going on. So this is actually a Git operation under the hood, and it's going to push refs which are stored in your .git directory to the GitHub repository. So don't put a remote here, a DVC remote here. It's really your Git remote, which is normally called origin, hence the name. Okay, and to pull experiments, you just do DVC X pull origin. You could do that directly in Git, but given that many people, including me, up to a couple of months ago, didn't know what Git refs actually were, basically it's easier to use this wrapper thing. Okay. Of course, don't forget to update your data if you want to reproduce an experiment. Don't forget to update the data rather than only the metadata. That's the usual thing which I already mentioned a couple of times. Okay, so what about, I'm not using Python, so what do I do with the DVC live module? Well, basically for R, there's no problem, because there is this very nice package, R package, reticulate, and that actually allows you to run Python code in R. So you just use the reticulate library, and then you import the DVC live module into an R variable, and then you can use it in order to do the same calls as there were before in this Python example. So for R, there is no problem. It's just a one-to-one translation. Okay, suppose that my simulation is a C++ program, for instance. Yeah, okay. I can use, for instance, Boost in order to run Python from within my C++ code. If your experiment is Fortran, I think you're going to be in for a very nice experience, because then you would have to go to C for something. No, so go to C for C++ for Boost, and then from C++ to Python using Boost, and okay, that's going to be an interesting experiment. But anyway, so from C++, it's still quite doable. From R, it's actually quite trivial. One thing that you should really not forget for R is this live end call. This is quite important. Okay, why am I emphasizing this here? And I didn't mention end for Python. Okay, remember what we did in Python? We created a context manager. The context manager is going to call end. You don't have to do it. It's automatic thanks to context management in Python. R doesn't have such a thing, so that means it's up to you to call live end. If you don't do that, files are not closed properly, data is not stored correctly, and your experimental data is at least partially corrupted. Okay. So combining experiments and pipelines, things get more and more complicated. So basically, you can use DVC live in conjunction with pipelines. So an experiment is essentially a stage, and that uses DVC live, okay, and then you keep track of dependencies, parameters, metrics, and so on, using the stages in your pipeline. So it all fits together. So this kind of brings that together. Okay, so experiments run in pipelines. So basically, the experiment itself is now going to be part of my pipeline. So I add a stage. This contains code that does calls to DVC live. So my Python script, my R script, whatever, is going to do DVC live. And the parameters, of course, should again be read from params.yaml. That is quite clear. So then you can run the experiment. So just DVC x run. Or I can run it with a parameter set on the command line, which would override whatever is in my YAML file. Okay. And then for a specific experiment, so for instance, to redo high A, whatever high A is, I can just do DVC X apply name of the experiment I want to redo, and then I can run it. Okay. So basically, if I override a parameter on the command line, then in fact it is going to change params.yaml. So again, if you like, you can record this in a commit using VSC, using Git. Sorry. Okay. Parameter sweeps. Anyone? Here they come. So basically, you can have queues of experiments. So basically, I can start a queue or add an experiment to a queue rather. So DVC x run --q is going to add that to the queue. So basically, that does not mean that it's executed. It's just submitted to the queue. Compare this a little bit, if you like, to a workflow. Sorry. A manager, a job manager, a scheduler on an HPC system. It's not going to schedule, it's just going to manage simple things, but still, it's the same in spirit. So I'm just going to queue a single experiment here, or I can queue a range of values. So basically, this is going to queue 3 experiments. One for A equal to 3, one for A equal to 4, one for A equal to 5. So that answers your question. Those will be 3 different experiments, and given all the query stuff and visualization stuff, so the plots, etc., you already know how to compare. So yeah, that's the answer to your question. And then once everything is queued, you can start running stuff by adding run all. Okay, I think this is a typo. I think this must be double dash there before the set parameters. I don't think there is a reasonable reason that it's missing. That would be slide 74. But I would have to double check the documentation, but I'm rather convinced that that is a typo. Okay, so basically, just like with Slurm, you can check the status of your queue, so DVC queue status, and then you see that all these guys here are queued, and that these were successfully run. You can check the logs. Basically, it gets some stupid name. That's the dopey thing here. Where's the dopey thing? Here's the dopey thing. So that is one particular instance of this experiment that has been queued, is finished. So I can check its log by using the name of that particular task. Tasks have names, they're random. So basically, that would give me the dopey Fang task, whatever. And that showed me the logs. So basically, this is maybe interesting for something that was successful, and certainly interesting for something that failed, because that allows me to check what went wrong, hopefully, in that particular task. Okay. If you want to run either queue task or complete a task, you can just do dvc queue remove, again, name of the task, easy. Okay, queue control. So basically, run all the tasks in the queue, and you can also fix the number of workers. So basically, a worker is going to run a task. So if I specify, in this case, jobs is 2, 2 computations, 2 tasks are going to run simultaneously. So this is a way to parallelize that kind of work. Of course, in HPC terms, this is parallelization on a single compute node. So there is, at this point at least, certainly nothing that would make sure that your tasks run on multiple nodes if they are part of your job, etc., etc. This is a single node thing. So that also means that the maximum number of jobs is of course determined by the number of cores in your machine. It does not make sense at all to have more jobs than cores in your CPUs. Simple. So basically for instance, Ice Lakes, that would be in our infrastructure 72. For Sapphire Rapids, that would be 96. Doesn't make any sense. Also, what you have to take into account is how many cores does an individual task use. If it's a simple Python script, probably just 1. But if under the hood I use something a bit smarter or whatever, then that might be more. So that means that the number of tasks times the number of cores that an individual task is going to use, that is going to be the number of jobs, that will determine the number of jobs at the end of the day. Okay, so that's important to keep in mind. Also keep in mind there is no such thing as spinning. So yeah, this is poor man's parallelization in HPC terms. How does it integrate with Slurm? Trivially, and hence primitively, and hence maybe not optimally or inefficiently. So essentially what you do is you have a job that runs on a single node. Okay, you ask for a number of tasks that's equal to jobs which you specify using this jobs flag here. Okay, then if an individual task uses multiple cores, the number of CPUs per task which you ask of Slurm should be that number. Basically, the number of tasks times the number of CPUs per task, if you multiply those, should not exceed the number of cores in your machine. Don't oversubscribe unless there is good reason to, and there may be reasons for that, but okay, let's not go there. Okay, so does that sort of answer your question? What is not happening is spinning. So basically, a task may migrate from cores to other cores, etc., etc. There is nothing here that could prevent that. DVC is not sophisticated enough to have any notion of that kind of HPC fine-grained stuff. So yeah, again, this is a poor man's parallelization. But yeah, you can do it. Okay, you can stop all the workers. You can stop and kill all the workers. So if you stop them, they're still around. So you can resume. If you kill them, yeah, then they die. You have to start over, whatever. And you can also kill a specific running task. That's also possible. Can be useful if you know this task will never complete successfully because the parameter is stupid. Or I'm monitoring, and from the metrics I see that that's not going anywhere. Then I can just kill that task and save some compute time. Okay. So basically, we are at the end, just imagine, and even within 4 hours, which is sort of great. So basically, I would say that DVC is an interesting system because you don't need any additional, you don't need infrastructure in a way. Just your HPC infrastructure as is going to do the job. And it is going to give you many things. It is going to give you a record of whatever is interesting during your experiments. It gives you a way to compare between experiments, parameter values, metrics, blah, 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 the whole thing. It gives you a way to redo experiments in a reproducible way. So it's actually a rather powerful thing. And you might have noticed the artifact, the safe artifact thing, which was in the DVC Live example. So basically, it also allows me to record my models, my trained models. So basically, I have those as well. I can put those, if I want, under DVC control, because they're just binary files, so that's just data in a way, for whatever definition of data you want to apply to that. But basically, I can put my trained models into my DVC repository, which means that if I combine that with the metadata I get out of my experiment recording stuff, which I can do with DVC, I actually have everything I need. I don't need to retrain my model if it's under DVC control, and I can get whatever version of the trained model if I find the commit in which this was, if I find the relevant commit. Because then I can retrieve with DVC the model and I can rerun, etc., etc. So essentially, you've got everything you need. Maybe not with such a nice bow tied around it, which you get with something like MLflow, but actually this does the job with zero infrastructure. Well, okay, with a lot of infrastructure, you have an HPC system, which is not exactly zero. You also need some storage somewhere, which is also not exactly zero, but you see where I'm going. I don't need any fancy setup. That's the big advantage, in my opinion. And that's why I like this in an HPC setting. And of course, again, this transcends machine learning. This goes for every experiment you do ever. So that also helps quite a lot. The end of the day is that you want reproducibility of experiments, of workflows, of data, etc., etc. And of course, it does facilitate sharing because everything, at the end of the day, is in your Git repository, wherever that lives, on GitHub, on GitLab, on-prem, or whatever. So basically, this is quite cute. What you need, of course, is discipline. You need to use version control, ordinary version control being Git, in a very disciplined way. And what is especially important is that your commits do the right thing. So when I give a training about version control with Git, one of the things I try to about one single change. That change may occur in 20 files, probably not, but it may occur in multiple files or in multiple places of a file, but it's an atomic thing. So it's something that you can write a description of in one sentence that does not contain the word and. Okay, if you have that discipline, if you know how to use Git in such a way, and sorry, but yeah, that's the proper way of using Git, so just learn it, then things are easy. Because then commits have very clear semantics and you know exactly what changed from one commit to the next, which means that you can restore your working environment in order to reproduce whatever you like, given that things are atomic. So that's quite important. And if you followed along while I was doing this, you may have noticed that in fact that was exactly what I was doing. Each time very clearly separating things that changed, doing multiple commits, although multiple things changed at the same time. I separated those into separate commits to make sure that the commit is a single thing, causes a single change. That's the important thing here. Okay, and then of course, now we have two things which work in tandem. On the one hand, we have Git. On the other hand, we have DVC. So yeah, I'll repeat it once more. If you change your metadata, don't forget to do a DVC checkout, or you work with the old data. Okay, so that's a bit probably the most dangerous pitfall here, that you simply forget to do that. Rerun your experiment, probably changing multiple things. Think you changed everything, only you forgot to change your data. Yeah, right. I mean, that's up to you, and that's a drawback here. This disconnect between, on the one hand, metadata and data. And unfortunately, at this point in time, it's you that has to do the bookkeeping. And keep in mind that a Git checkout on your DVC metadata file implies that you really need to do a DVC checkout to bring things back in sync. Okay. All right. So references. The Git documentation, as you know, is quite good. I really like it. ChatGPT is your friend with respect to Git. GitHub Copilot is definitely your friend with respect to Git. It knows quite a lot about it for some reason. And the DVC documentation is okayish. It's quite reasonable. You have to read between the lines many times, but basically the documentation itself is quite reasonable. Okay. Why is this here? Okay, we can start over, I think. Ah, that's nice. Okay. Okay, this is weird. Never seen this before. Never mind. So basically, that's the end of the training as far as I'm concerned, unless there are questions. Question online. Would it be possible to use certain jobs as backends to execute the different stages? Yeah, theoretically, you can do that. So basically, in theory, a stage could be a job submission. There is nothing that says that you cannot do that. But of course, that would be interesting, since somehow you would need to make sure that when a job gets submitted, that it has a dependency on previous jobs. So you can get that done, but it would be a very manual thing to do. And it would be something that is, unless you sit down, think for quite a while to do it right, would be very error prone. But in theory, it can be done. The problem is there's no direct support for this. So if you look at Nextflow, Nextflow does have direct support for a mixed pipeline or a pipeline that's entirely realized using Slurm jobs. So that is built into Nextflow. I'm hoping that DVC will go that route at some point, but as far as I know, it's not there at this point. I also don't know whether there are plans to do that. My impression, while I was talking to the DVC people, is that they are less aware of HPC. Let me put it that way. Which means that they are more aware of cloud and other providers, which makes sense from their point of view. But basically, it was pretty clear during that conversation that they have a different outlook on machine learning experiments than we as HPC users have. Who knows? Other questions? Okay. If not, we conclude. Thanks for being here, and I hope to see you in some other training at some later point. If you have questions at any time, feel free to mail me. No problem. Okay, so again about the recording, it will be available probably by this evening. If you want access, drop me a line, an email, and I'll send you the link. Okay. And that was it. It's probably the first training ever that I finished in less than 4 hours. So there is hope yet.
Thank you very much.
My pleasure. I hope it was useful.